Chapter 1, Introduction, The Tectonic Shift to Software 3.0. Sections. Section 0.1, Why Syntax Memorization is no longer the gatekeeper. Section 0.2, Defining Software 1.0, 2.0, and the New Era of Natural Language Programming. Section 0.3, The Rise of the AI Native Developer, Orchestration over Typing. Section 0.4, How to Use This Book, a Roadmap from Absolute Beginner to System Architect. The discipline of software engineering is currently undergoing a macroeconomic and technological tectonic shift. If you picked up this book because you heard that coding is dead or that AI will replace programmers, I want you to pause and reframe that narrative immediately. Coding isn't dying, it is evolving into something far more powerful. We are witnessing the transition from Software 1.0, where humans laboriously typed every single instruction, to Software 3.0, where we guide intelligent systems to generate those instructions for us. For decades, the path to becoming a developer was a steep, rocky climb. You had to memorize obscure syntax, fight with missing semicolons, and spend months learning how to speak the computer's language. Today, that dynamic has inverted. The computer has finally learned to speak our language. This book is not just about using ChatGPT or Claude to write code. It is a manifesto for the AI native developer. It is about skipping the years of rote memorization and jumping straight into the high-leverage work of system design, logic architecture, and product creation. Welcome to the new era of building software. 0.1 Why Syntax Memorization is no longer the gatekeeper. For the last 40 years, the gatekeeper of the software industry was syntax. If you didn't know whether to use a curly brace or a square bracket in JavaScript, the computer simply refused to talk to you. You could have the most brilliant idea for an app, but if you couldn't type the specific incantations required by the compiler, your idea remained an idea. In Software 3.0, syntax is a commodity. It is cheap, abundant, and instantly generated. The modern large language model, LLM, has indexed nearly every line of public code ever written. It knows every bracket, every indentation rule, and every library import. Because of this, the value of a developer has shifted from how fast can you type correct Python to how clearly can you define the problem you want to solve. This shift is liberating, but it also removes the safety net of rote learning. In the past, you could get a job just by proving you knew the syntax. Now, you must prove you understand the system. How to Code with AI: The Absolute Beginner's Guide to Building Software Without Memorizing Syntax. Docx. You are no longer a bricklayer, manually stacking stones one by one. You are now the architect, directing a team of incredibly fast, but occasionally confused, robotic bricklayers. Your job is to ensure the wall is built in the right place, not to lift every brick yourself. 0.2 Defining Software 1.0, 2.0, and the New Era of Natural Language Programming. To navigate this new world, you must understand the history of the terrain. We categorize software development into three distinct epochs. Software 1.0, the era of explicit instructions. This is the traditional programming you likely picture in your head. A human writes explicit logic: if the user clicks this button, turn the background blue. This requires the human to account for every possible edge case. It is deterministic, precise, and brittle. If you forget to tell the computer what to do when the user clicks the button twice, the program might crash. Software 2.0, the era of learned weights. This emerged with the rise of deep learning and neural networks. Instead of writing explicit rules, like if the image has whiskers, it's a cat, programmers curated massive datasets of cat photos and trained a model to recognize the pattern mathematically. The code wasn't written by a human, it was learned by the machine as a set of floating point numbers, weights. This was powerful but largely restricted to data scientists and mathematicians. Software 3.0, the era of natural language intent. This is where we are today. Software 3.0 bridges the gap. you use natural English, or any language, to describe your intent, and a transformer model translates that intent into the code required to execute it. Consider the difference in workflow. Software 1.0 approach, you spend 2 hours reading documentation on how to center a development in CSS, type the code, refresh the browser, see it's wrong, and try again. Software 3.0 approach, you type, create a responsive card layout where the content is perfectly centered and uses a soft shadow, and the AI generates the CSS instantly. The barrier to entry has collapsed. However, the barrier to mastery has moved. You no longer need to speak computer, but you must become distinctively articulate in describing logic. 0.3 The rise of the AI native developer, orchestration over typing. You are entering the field at a unique historical moment. You are not competing with senior developers who have 10 years of experience in manual coding. You are part of the first cohort of AI native technologists. Employers are realizing that a junior developer who knows how to effectively orchestrate AI tools is often more productive than a mid-level developer who stubbornly refuses to adapt. But this comes with a warning. There is a dangerous trap known as a vibe coding, the act of blindly copy-pasting code from an AI because it looks right or vibes correctly, without understanding what it does. Research from Anthropic and various field studies suggests that juniors who rely on AI as a crutch, generating code without reading it, see a degradation in their learning retention. They build houses of cards that collapse the moment a bug appears. To succeed, you must adopt the mindset of an orchestrator. The architect, you define the inputs, outputs, and requirements. The auditor, you review the RA's work for security flaws and logical errors. The integrator, you stitch together different pieces of code into a cohesive application. The AI is your junior partner. It is enthusiastic and incredibly fast, but it is prone to hallucination. It will confidently lie to you. Your role is to be the human in the loop, the verifying force that ensures quality. 0. For how to use this book, a roadmap from absolute beginner to system architect. This book utilizes the CIVE Framework, context, intent, verification, execution, a methodology I developed to ensure you learn the principles of engineering, not just the shortcuts. We will not spend chapters memorizing variable types or drilling syntax for loop structures. Instead, we will focus on high-level orchestration. Here is how we will proceed. Part 1. The new rules establishes your environment. You will set up tools like VS Code, Cursor, and GitHub Copilot. We will tackle the psychology of learning in the age of AI. Part 2. The CIVE Foundation is the core of the book. You will learn context engineering, how to teach the AI what you want, intent specification, how to think before you prompt, and most importantly, verification, how to debug when the AI inevitably messes up. Part 3, Fundamentals you still need covers the 20% of computer science that you absolutely cannot outsource to a robot. You need to understand data structures and security, or you will be helpless when the AI generates bad code. Part 4, Building the portfolio is pure action. We will build real applications, not just hello world, but functional, deployed software. We will conclude with career strategies for the post-agile job market. The goal of this book is not to teach you how to type. The goal is to teach you how to think. By the end, you will not just be a person who uses AI, you will be a software engineer who wields AI to build things that were previously impossible for a single individual to create. Figure, extra detailed AI-ready prompt for AI-generated diagram showing the CIVE cycle as a circular flow chart. The 4 quadrants are: 1. Context, input icon, setting the stage. 2. Intent, target icon, defining the goal. 3. Execution, lightning bolt icon, AI generation. And 4. Verification, magnifying glass icon, human review. Arrows flow clockwise. In the center of the circle is the text, the AI native loop. The style should be modern, clean technical infographic, utilizing a blue and teal color palette. Turn the page. Let's start building. Figure mind map, the tectonic shift to software 3.0 root, the tectonic shift to Software 3.0, branch, evolution of software, node, Software 1.0, explicit instructions, node, Software 2.0, neural weights, node, Software 3.0, natural language intent, branch, the syntax gatekeeper, node, old barrier, memorization, node, new barrier, logical specification, node, goal, architect versus bricklayer, branch, the AI native developer, node, role, orchestrator, node, role, auditor, node, trap. Vibe coding or blind copying, branch, the CIVE Framework, node, context, setting the stage, node, intent, defining the goal, node, verification, debugging review, node, execution, AI generation. Chapter 1, the AI native mindset and the death trap. Sections. Section 1.1, the double-edged sword, understanding the 17% mastery gap. Section 1.2, crutch versus tutor, recognizing passive reliance versus active learning. Section 1.3, cognitive offloading, when to delegate and when to dig in. Section 1.4, the human in the loop, why your logic is the ultimate safety net. Welcome to the new frontier of software engineering. If you read the introduction, you know that the tectonic plates of technology have shifted. We have moved from the era of manual syntax authorship to the era of AI orchestration. However, before we write a single line of code or generate our first prompt, we need to have a serious conversation about how you learn. In traditional coding boot camps, the biggest risk was burnout, students quitting because they couldn't memorize syntax fast enough. In the age of AI, the risk has inverted. The danger isn't that you will get stuck and quit, the danger is that you will succeed too easily. You will build apps that work, features that function, and interfaces that look beautiful, all without understanding a single variable under the hood. This is what I call the AI death trap. It is a comfortable, seductive illusion of competence that can cripple your career before it begins. To become a true AI native developer, you must understand the difference between using AI as a tool for leverage and using it as a replacement for thinking. 1.1 The double-edged sword, understanding the 17% mastery gap. Generative AI is the most powerful force multiplier developers have ever seen. It can turn a junior developer into a senior architect, or it can turn them into a liability who creates code they cannot maintain. The difference lies entirely in the mindset of the operator. Recent research has quantified this danger. A study involving junior developers revealed a startling statistic: those who relied heavily on AI tools to complete tasks without active engagement saw a 17% decrease in skill mastery compared to their peers. To put that in academic terms, 17% is the difference between an A student and a C student. It is the difference between passing a technical interview and being politely shown the door. Figure, a clean, minimalist bar chart comparing active learners versus passive copiers. The active learners bar is high and green, labeled deep understanding. The passive copiers bar is 17% lower and colored cautionary orange, labeled surface level illusion. The background is white with soft gray grid lines. Why does this gap exist? It comes down to productive struggle. Neuroscience tells us that learning happens when the brain is forced to bridge a gap between what it knows and what it needs to solve. That moment of frustration, where you stare at an error message and think hard, is when the neural pathways for logic are built. When you copy-paste an error into ChatGPT and blindly paste the solution back into your editor, you short-circuit that learning loop. You solved the immediate problem, but you robbed yourself of the lesson. You are renting intelligence rather than building it. 1.2 Crutch versus tutor, recognizing passive reliance versus active learning. The goal of this book is not to scare you away from AI. We want you to use it constantly. But we need to change how you use it. You must shift your relationship with the LLM, large language model, from that of a solution machine to that of a Socratic tutor. Let's look at two scenarios to illustrate the difference. The crutch approach, passive reliance. You want to center a button on a web page using CSS. User prompt, write code to center a button in a division. AI output. Div. Display, flex. Justify content, center. Align items, center. Result, you paste the code. It works. You move on. Learning outcome, 0. If the layout breaks next week, you won't know why flex was used or how to fix it without asking the AI again. The tutor approach, active learning. You have the same problem, but you use the AI to build your mental model. User prompt, I need to center a button. I know Flexbox is a modern way to do this. Can you explain the difference between justify content and align items conceptually first, and then show me the syntax? AI output, the AI explains that justify content handles the main axis, horizontal, usually, and align items handles the cross-axis, vertical. It uses an analogy of beads on a string. Result, you read the explanation, write the code, and verify it works. Learning outcome, high. You now understand the concept of axes in layout design. You are building a mental library of logic that exists independently of the tool. Figure, a split-screen illustration showing a developer on the left labeled the crutch blindly catching fish thrown by a robot, while the developer on the right labeled the tutor is being guided by the robot on how to hold a fishing rod. The lighting is warm and encouraging. The rule of thumb is simple, never paste code you cannot explain. If the AI generates a solution using a function you've never seen, your next prompt must be, explain how that specific function works. 1.3 Cognitive offloading, when to delegate and when to dig in. In cognitive psychology, cognitive offloading refers to using physical actions or external tools to reduce the mental demand of a task. Writing a grocery list is cognitive offloading. Using a calculator is cognitive offloading. For the AI native developer, success comes from knowing exactly what to offload. We want to offload the tedious, low-value work so we can focus our brainpower on high-value system design. Safe to offload, the how * syntax specifics, how do I write a for loop in Python versus JavaScript? * boilerplate, set up the basic folder structure for a React app * rejects and patterns, write a regular expression to validate an email address. * CSS memorization, what is the hex code for a dark navy blue? Dangerous to offload, the what and why in * business logic, decide how we should calculate tax rates for international customers. * system architecture, build the whole database schema for me. Without you reviewing the relationships. * security, handle user authentication. If you don't check for vulnerabilities, the AI might hallucinate an insecure method. Think of your brain as a CEO and the AI as your team of interns. You can tell the interns to file the paperwork, syntax, but you cannot tell them to set the company strategy, logic, without reviewing every detail. If you offload the logic, you are no longer the software engineer. You are just the typist. 1 point for the human in the loop, why your logic is the ultimate safety net. There is a prevalent myth that AI never makes mistakes. This is dangerous. Large language models do not know facts, they predict the next likely word based on statistical probability. They are prone to hallucinations, confidently stating things that are completely false. This is where your value lies. As an AI native junior developer, your primary role shifts from writing code to verifying logic. You are the human in the loop. Imagine an AI suggests a Python library to solve a problem. It looks correct. It runs without errors. But perhaps that library hasn't been updated in 4 years and contains critical security flaws. The AI doesn't care about security, it only cares about completing the text pattern. You must be the safety net. You must cultivate a healthy skepticism of every output. This requires a shift in identity. You are not learning to code to appease a compiler, you are learning to code so you can audit the machines. When you understand the fundamentals of data structures, loops, and conditional logic, which we will cover in Part 3, you gain the superpower of discernment. In the chapters that follow, we will introduce the CIVE Framework, context, intent, verification, execution. This is the methodology that keeps you safe. It ensures that you remain the pilot of the aircraft, using the autopilot to fly smoothly, but keeping your hands ready on the yoke for when the turbulence hits. The death trap is real, but it is avoidable. By committing to active learning, refusing to use AI as a crutch, and maintaining ownership of the logic, you will not just survive the AI revolution, you will lead it. Figure, mind map, the AI native mindset, central idea, the AI native mindset, branch, the danger, node, the 17% mastery gap, node, illusion of competence, node, the death trap, branch, learning strategy, node, tutor versus crutch, leaf, active questioning, leaf, concept first, node, productive struggle, leaf, neural pathways, leaf, don't short circuit, branch, cognitive offloading, node, good offloading, leaf, syntax, leaf, boilerplate, leaf, rejects, node, bad offloading, leaf. Business logic, leaf, security, leaf, architecture, branch, human role, node, verification, node, skepticism, node, logic owner. Chapter 2. Configuring your command center. Sections. Section 2.1, Beyond the Chatbot, Setting up Integrated Development Environments, IDEs, with AI. Section 2.2, Tool Selection Strategy, Cursor, GitHub Copilot, and Local LLMs. Section 2.3, Managing Privacy and Cost in a Token-Based Economy. Section 2.4, The Hello World of the AI Age, Your First Environment Verification. You have the mindset. You understand the death trap. You are ready to stop typing syntax and start orchestrating logic. Now, we need to build the workshop where this magic happens. If you have been relying on a web browser, opening ChatGPT or Claude in a tab and copy-pasting code into a text file, you are working like a tourist. You are visiting the land of code, but you aren't living there yet. To become an AI native developer, you must move from a visitor's pass to a permanent residence. We call this residence the Integrated Development Environment, or IDE. In the past, setting up an IDE was a rite of passage involving hours of configuration and cryptic error messages. In the Software 3.0 era, your IDE is something different entirely. It is a cockpit. This chapter is about establishing your command center. We will move beyond the chatbot window and integrate AI directly into your file system. By the end of this chapter, you won't just be chatting with an AI, you will be piloting a system where the AI can read your files, understand your project structure, and edit code alongside you. 2.1 Beyond the Chatbot, Setting up Integrated Development Environments, IDEs, with AI. The single biggest friction point for beginners using web-based AI interfaces is context loss. When you paste a snippet of code into ChatGPT, the AI only knows what you just pasted. It doesn't know about the file next to it, the folder structure above it, or the variable definitions you wrote 3 days ago. To compensate, beginners often find themselves pasting huge blocks of text back and forth, playing a messy game of telephone. This is inefficient and error-prone. The solution is an AI-integrated IDE. An IDE is a specialized text editor that includes tools for building software, debugging, terminal access, file management. When we embed AI into the IDE, we grant the AI vision. It can see your entire project folder. Figure, a split-screen diagram comparing the tourist workflow vs the command center. Left side shows a user frantically copy-pasting between a web browser and a notepad file with arrows indicating data loss. Right side shows a sleek dark mode IDE interface where the AI chat window is docked inside the editor, with lines of sight connecting the AI to multiple files in the project tree, representing shared context. Style, clean, isometric technical illustration, blue and orange accent colors. When you ask an IDE embedded AI to fix the bug in the login function, you don't need to paste the code. The AI simply looks at the file, identifies the function, and suggests the change directly in the editor. This shift changes your role from courier, moving text around, to commander, issuing directives. 2.2 Tool Selection Strategy, Cursor, GitHub Copilot, and Local LLMs. The market for AI coding tools is exploding. As a beginner, you do not need to try them all. You need one reliable stack that works out of the box so you can focus on the CIVE framework. Here is the strategic landscape of the tools available to you right now. The AI native disruptor, Cursor. For the absolute beginner in 2024 to 2025, Cursor is the recommended starting point. Cursor is a fork of VS Code, the industry standard editor, which means it looks and feels exactly like the standard tools used by professionals. However, Cursor was rebuilt with AI as the primary interface, not an afterthought. It allows you to *highlight code and press CMD+K or Ctrl+K to instruct the AI to change it. *chat with your entire code base, e.g., where is the user database defined? *accept tab completions that predict the next few lines of logic. Because it is built on VS Code, any tutorial you find for VS Code applies to Cursor. It gives you the best of both worlds, industry standards and cutting-edge AI integration. The enterprise standard, VS Code plus GitHub Copilot. If you are entering a strict corporate environment, you will likely encounter Microsoft's Visual Studio Code, VS Code, paired with the GitHub Copilot extension. This is a robust combination. VS Code is the editor, and Copilot is the plugin. While it is powerful, the integration is slightly less fluid than Cursor because Copilot is an add-on, not the foundation. It excels at autocomplete, predicting what you are typing in real time, but sometimes lags in agentic tasks like refactoring multiple files at once. The privacy option, local LLMs, Ollama plus Codia continue. For those concerned about sending data to the cloud, or those with powerful gaming PCs, specifically with NVIDIA GPUs, running a local large language model, LLM, is an option. Tools like Ollama allow you to run models like Llama 3 or Mistral directly on your hardware. You can then connect these local models to VS Code using extensions like Continue or Sourcegraph Cody. Recommendation: unless you have a specific privacy requirement or a high-end GPU, start with Cursor. It removes the friction of setup and lets you focus immediately on learning logic. 2.3 Managing privacy and cost in a token-based economy. Before we launch the software, we must discuss the economics of your command center. In Software 3.0, code is generated by tokens. A token is roughly equivalent to 0.75 of a word. Every time you ask the AI a question, and every time it replies, meters are running. Most professional tools, like Cursor or Copilot, operate on a subscription model, approximate $20 per month. For a career switcher, this is the highest ROI investment you will make. It costs less than a single textbook and provides an infinite tutor. The privacy red line. When you use cloud-based AI, your code snippets are sent to servers, usually hosted by OpenAI, Anthropic, or Microsoft, for processing. As a beginner, you must adhere to one golden rule regarding privacy. Never put secrets in the chat. Secrets include *API keys, passwords that let your app talk to other services. *database passwords. *personal identifiable information, PII of real users, names, emails, credit cards. If you are building a practice app, this is rarely an issue. But you must build the muscle memory now. Treat the AI chat window like a public whiteboard in a coffee shop. Don't write anything on it that you wouldn't want a stranger to see. Context window management. Cost isn't just about money, it's about attention. LLMs have a context window, a limit on how much text they can remember in a single conversation. If you have a chat that runs for 3 days, the AI will eventually forget the instructions you gave it at the beginning. This leads to hallucinations and bad code. The strategy: treat chat sessions as disposable. Once you have solved a specific problem, e.g., create the login page, close that chat and start a fresh one for the next task. This keeps the AI's attention sharp and prevents it from getting confused by old, irrelevant instructions. 2. For the hello world of the AI age, your first environment verification. In traditional programming books, your first task is to make the computer print hello world. That proves the language is installed. In the AI age, printing text is trivial. Our hello world is different. We need to verify that your command center is properly connected, that the AI can see your files, understand your intent, and execute a change. Follow this sequence to perform your initial system check. Step 1. Create the workspace. Open your chosen IDE, e.g., Cursor. Do not just open a file, open a folder. AI tools rely on folder structures to understand context. Create a folder on your desktop named AI_first_flight and open it in the editor. Step 2. The blank slate. Create a new file named mission.py. Leave it completely empty. Step 3. The verification prompt. Open the AI chat pane, usually on the right side. We are going to use a specific prompt to test the AI's vision. We won't copy-paste anything. Type this command. I have created a file named mission.py. Please verify you can see this file. If you can, write a Python script inside it that calculates the Fibonacci sequence up to the 10th number and prints the result. Do not just tell me the code, apply the edit to the file. Step 4. Verification. If the system is configured correctly, two things will happen. 1. The AI will confirm it sees the file. 2. You will see ghost text or a difference view appear in your empty mission.py file, showing green lines of code waiting to be accepted. Click Accept or CMD plus Enter. Now, run the code. In your terminal, inside the IDE, type Python mission.py. If the terminal outputs the sequence 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, congratulations! You have just completed your first loop of the CIVE framework. Context, the AI read your file structure. Intent, you specified the logic, Fibonacci. Verification, you ran the script to confirm the math. Execution, the code is saved. You are no longer a tourist. You have a command center. Now, we must learn how to speak the language of the machine so we can give it instructions that are actually useful. Figure Mind Map Chapter 2, Configuring Your Command Center, Software 3.0 Workspace, the goal, from tourist to resident, the problem, context loss in browsers, IDE selection, cursor, AI native, best for beginners, VS Code plus Copilot, enterprise standard, local LLMs, privacy focused, the economics, tokens equals cost to compute, the privacy red line, no secrets API keys, context window, keep chat short and focused, the AI hello world, 1. Create workspace folder, 2. Create empty file, 3. Prompt, verify vision and apply edit, 4. Run and confirm. Chapter 3, CIVE Phase 1, Context Engineering. Sections. Section 3.1, the concept first prompt, forcing the AI to teach before it codes. Section 3.2, priming the engine, defining your skill level and learning goals. Section 3.3, managing the context window, how to feed project requirements effectively. Section 3.4, iterative refinement, steering the conversation away from hallucinations. You have configured your environment. Your IDE is installed, your API keys are set, and your command center is ready. You are staring at a blinking cursor or an empty chat window. This is the moment where most beginners make a critical mistake. They type, "Write me a snake game in Python." The AI will happily oblige. It will spit out 50 lines of code that work perfectly. You paste it, run it, play the game for 30 seconds, and feel like a wizard. But you aren't a wizard. You are a passenger. You haven't learned anything, and if the code breaks, you won't know how to fix it. This approach bypasses the learning process entirely. To succeed in Software 3.0, you must stop treating the AI as a vending machine and start treating it as a brilliant but literal-minded junior colleague. You need to provide it with the right background information before you ever ask for a specific task. We call this context engineering. It is the first pillar of the CIVE framework: context, intent, verification, execution. Context engineering is the art of setting the stage, defining the roles, and establishing the constraints of the conversation to ensure the AI teaches you, rather than just doing the work for you. 3.1 The concept first prompt, forcing the AI to teach before it codes. The most dangerous thing an AI can do for a beginner is give them the answer immediately. When you see the solution before you understand the problem, your brain skips the crucial step of conceptual mapping. You recognize the syntax, but you don't understand the logic. To counter this, you must adopt the concept first prompt. This pattern flips the script. Instead of asking for code, you explicitly forbid the AI from writing code until it has explained the underlying computer science principle. You are forcing the AI to act as a tutor, not a generator. Here is the difference between a standard prompt and a concept-first prompt. The standard, lazy prompt: how do I download data from a website using Python? The concept-first prompt: I want to download data from a website using Python, but I am a beginner. Do not write any code yet. First, explain the concept of an HTTP request and an API. Use an analogy to help me understand how my computer talks to a server. Once I confirm I understand, then we can look at the code. When you use the second prompt, the AI shifts gears. It stops trying to be a code completion engine and starts acting like a teacher. It might explain that an API is like a menu at a restaurant, and the request is you ordering a meal. Only after you read that explanation should you type, "Okay, I understand. Now show me the simplest Python code to make that request." By sandwiching the code between the concept and the execution, you ensure that you are actually learning the logic of the system. Figure: extra detailed AI-ready prompt for AI-generated diagram showing a split-screen comparison. On the left, a lazy prompt leads to a black box output where the user looks confused. On the right, a concept-first prompt shows a flow: user asks for concept-AI displays a lightbulb icon, a diagram-a user confirms-AI displays code-user looks enlightened. The style should be clean, modern line art with blue and orange accent colors. 3.2 Priming the engine, defining your skill level and learning goals. Large language models, LLMs, like GPT-4 or Claude are shapeshifters. They can speak like a PhD researcher, a marketing copywriter, or a surly teenager, depending on how you talk to them. If you don't define who they should be, they will default to a generic, encyclopedic tone that is often too dense for beginners. You must prime the engine by explicitly defining two personas, the AI's persona and your own. Defining the AI's persona, tell the AI exactly who it is. Do you want a strict professor? A supportive coding buddy? A senior engineer conducting a code review? Defining your persona, tell the AI who you are. Are you a complete novice? Do you know Excel formulas but not Python? Are you a visual learner? Consider this system priming prompt that you can use at the start of every new project or chat session. You are a senior software architect acting as a mentor. I am an absolute beginner with zero coding experience. Your goals are: 1. To help me build a to-do list app. 2. To ensure I understand *y*, we are doing things, not just *how*. 3. To prioritize clean, readable code over complex, advanced shortcuts. Constraints. Explain technical jargon like arrays or functions using real-world analogies. If I ask for a solution, give me a hint first, then the code only if I am still stuck. By pasting this into the chat window before you begin, you set the parameters for the entire interaction. The AI will now structure its responses to match your current mental model, saving you from being overwhelmed by technical vocabulary you aren't ready for yet. 3.3 Managing the context window, how to feed project requirements effectively. One of the biggest limitations of AI is its context window. Think of this as the AI's short-term memory. It can only remember a certain amount of conversation before it starts forgetting the beginning. If you are building a complex application, you cannot just ramble endlessly. You need to be disciplined about what information you feed into the context window. Garbage in, garbage out applies heavily here. If you feed the AI vague requirements, you will get vague, buggy code. To manage the context effectively, you should provide a tech stack and goal summary at the start of a session. This acts as an anchor for the AI. Here is a template for setting the technical context. Project context. Goal: build a simple currency converter website. Languages: HTML, CSS, and Python, using Flask. Current state: I have the HTML file created, but I don't know how to connect it to Python. Constraints: use the free exchange rate API for data. Do not use a database yet. By providing this structured block, you prevent the AI from hallucinating a solution that uses technologies you aren't using, like React or Node.js. You are fencing in the AI's creativity so that it focuses entirely on the specific tools you are trying to learn. If the conversation gets too long and the AI starts making mistakes or forgetting your previous instructions, it is time to flush the context. Start a new chat, paste your system priming prompt from section 3.2 and your project context summary, and continue from there. This keeps the AI's reasoning sharp. Figure: extra detailed AI-ready prompt for AI-generated diagram showing a context window visualization. It depicts a funnel where a vague inputs spill over the sides, while structured context, represented by neat blocks labeled goal, stack, constraints, fits perfectly into a processor, resulting in a clean diamond output. Use a schematic, engineering blueprint style. 3-point for iterative refinement, steering the conversation away from hallucinations. Even with the best context engineering, the AI will eventually veer off course. It might suggest a library that hasn't been updated in 3 years, or it might write code that is far too advanced for your current level. This is where you must practice iterative refinement. You must be the captain of the ship. If the AI gives you a response that feels wrong, confusing, or overly complex, do not blindly accept it. Pushback. Here are 3 common correction prompts you will use constantly. The too complex to correction. Prompt: you used a lambda function here. I don't know what that is. Rewrite this code using a standard loop so I can understand the logic better. The hallucination check. Prompt: you imported a library called Simple Weather. Are you sure this is a standard library? Please double check. I want to use the standard requests library instead. The step back request. Prompt: we are moving too fast. I am lost on the last step. Please stop writing code and explain the logic of lines 10 through 15 in plain English. Remember, the AI does not have feelings. You cannot offend it. If it gives you bad advice, correct it immediately and authoritatively. This process of correction is actually where deep learning happens. By analyzing why the AI's suggestion was too complex or incorrect, you are sharpening your own engineering judgment. Context engineering is about taking control. It is the realization that the AI works for you, not the other way around. Once you master the ability to set the context, prime the persona, and manage the scope, you are ready to move to the next phase of the CIVE framework, defining your specific intent. Figure mind map, CIVE Phase 1, Context Engineering Branch 1, Concept First Prompt Node, Forbid Code Initial Node, Demand Analysis Node, Verify Understanding Before Execution Branch 2, Priming the Engine Node, AI Persona, Mentor Senior Dev Node, User Persona, Beginner a Visual Learner Node, Setting Constraints Branch 3, Context Window Node, Short-Term Memory Limits Node, Structured Input, Goal, Stack, State, Node, Flushing Context, New Chat, Branch for the Iterative Refinement Node, Reject. Complexity Node, Check Hallucinations Node, Steering the Tutor. Chapter 4, CIVE Phase 2, Intent-Driven Specification. Section 4.1, Thinking Before Prompting, The Lost Art of Requirement Gathering. Section 4.2, Spec-Driven Development, using Gherkin syntax to define behavior. Section 4.3, inputs, outputs, and edge cases, eliminating ambiguity mathematically. Section 4.4, from vague ideas to rigid blueprints, a pre-code checklist. Sections. Section 4.1, thinking before prompting, the lost art of requirement gathering. Section 4.2, spec-driven development, using Gherkin syntax to define behavior. Section 4.3, inputs, outputs, and edge cases, eliminating ambiguity mathematically. Section 4.4, from vague ideas to rigid blueprints, a pre-code checklist. In Chapter 3, we discussed context engineering, the art of setting the stage for your AI partner. We learned how to define your role, the RA's persona, and the technological constraints of your project. You have successfully taught the AI who it is and where it is working. Now, we face a harder challenge, telling the AI what to do. This sounds deceptively simple. Most beginners sit down at their command center, open a chat window, and type something like, "Make me a website for my dog walking business." This is the digital equivalent of walking onto a construction site, handing a contractor a pile of lumber, and saying, "Build me a house." The contractor will build a house. But will it have a bathroom? Will the front door face the street? Will it collapse if the wind blows harder than 20 miles per hour? If you don't provide a blueprint, the contractor is forced to guess. In Software 3.0, the AI is a hyper-efficient contractor. It will guess instantly, and it will often guess wrong. To move from vibe coding to engineering, you must master intent-driven specification. You must stop asking for code and start defining behavior. For point 1, thinking before prompting, the lost art of requirement gathering. The single most valuable hour you will spend on your software project is the hour you spend away from the keyboard. A common symptom of the AI death trap is the urge to rush into the prompt. The blinking cursor creates anxiety. You feel productive only when text is streaming onto the screen. However, generating code based on a vague idea creates the technical debt instantly. You end up with a sprawling mess of logic that you don't understand and didn't ask for. Requirement gathering is the process of translating a fuzzy human desire into a concrete set of rules. Imagine you want to build a search feature for a recipe app. The vague prompt, write code to search for recipes. The hidden ambiguity, asterisk, does it search by title? By ingredient? By cooking time? Asterisk, what happens if no results are found? Asterisk, is it case sensitive? Doesn't pasta match pasta? Asterisk, does it happen instantly as I type, or only when I hit enter? If you don't decide these things, the AI will decide them for you based on statistical probability. It might give you a complex database search when you only needed a simple list filter. Before you engage the AI, you must engage your own logic. You need to articulate the intent. This is not about knowing Python or JavaScript syntax, it is about knowing exactly what you want the software to achieve. Figure, a split-screen comparison illustration. On the left side, labeled the vague prompt, a user types build a login and the AI generates a confusing, tangled knot of wires and unmatched doors. On the right side, labeled intent-driven specification, a user holds a blueprint labeled inputs and outputs, and the AI constructs a clean, modern, perfectly aligned secure doorway. The lighting should be clean and diagrammatic, emphasizing order versus chaos. For point 2, spec-driven development, using Gherkin syntax to define behavior. How do we communicate strict logic without knowing code syntax? We use a format that bridges the gap between human language and machine logic. The industry standard for this is Gherkin syntax. Originally designed for automated testing frameworks like Cucumber, Gherkin is the perfect tool for the AI native beginner. It forces you to structure your intent using 3 specific keywords: given, when, and then. This structure forces you to think linearly about cause and effect. The structure, asterisk given, the initial state of the system, context. Asterisk when, the specific action the user takes, trigger. Asterisk then, the expected outcome, result. Let's revisit that login feature. Instead of asking for a login page, we write a spec. Feature, user login. Scenario, successful login. Given the user is on the login page, and the user has a valid registered account. When the user enters their valid email and password, and clicks the Sign In button, then the system should validate the credentials against the database, and redirect the user to their personal dashboard, and display a Welcome Back notification. Do you see the difference? This creates a rigid boundary for the AI. It knows exactly what success looks like. Now, let's look at the failure scenario. Beginners often forget this, but software breaks more often than it works. Scenario, failed login, wrong password. Given the user is on the login page. When the user enters a valid email but an incorrect password, and clicks the Sign In button, then the system should remain on the login page, and display an error message saying invalid credentials in red text, and clear the password field but keep the email field filled. By writing this out before you prompt, you have done the heavy lifting of engineering. You can paste these Gherkin scenarios directly into your AI prompt. The prompt strategy: I want to implement a login feature in Python using Flask. Here is the Gherkin specification for the desired behavior. Please generate the code to satisfy these scenarios. When you provide this level of specificity, the AI stops hallucinating features you didn't ask for and focuses on implementing exactly what you need. For point 3 inputs, outputs, and edge cases, eliminating ambiguity mathematically. At a microscopic level, all software is just data transformation. You put data in, input, something happens, processing, and different data comes out, output. To master intent-driven specification, you must learn to think in I/O, input, output, pairs. If you ask an AI to write a function that calculates a tip at a restaurant, you must define the inputs. Is the input just the bill amount? Or is it the bill amount and the tip percentage? The happy path is the scenario where everything goes right. Asterisk input, bill, $100, tip, 20% asterisk output, $20. The edge case is an edge case is a situation that occurs at the extreme operating parameters of your system. This is where junior developers and AI models usually fail. If you don't specify how to handle edge cases, the AI will often write code that crashes your application. You must explicitly tell the AI how to handle the weird stuff. Consider these edge cases for our tip calculator. Negative numbers. What if the user enters -$50? Intent, the system should raise an error or convert it to absolute value. 0, what if the bill is $0? Intent, return $0. Text input, what if the user types $10? Intent, the system should prompt the user to enter numbers only. When you construct your intent, use a simple table format to clarify these rules for the AI. Function, calculate tip. Scenario input, bill, tip percent, expected output note. Standard 100, 2020 normal calculation. Low bill 5, 21 small numbers. 0 tip 100, 00 cheap customer. Negative -100, 20 error, invalid amount edge case. Decimal 10.50, 22.10 handle floats. If you paste this table into your prompt, the AI will write code that includes if-else statements to handle the errors. It creates robust, professional-grade code because you provided robust, professional-grade intent. Figure, a diagram of a black box function machine. On the left, a conveyor belt feeds distinct blocks labeled inputs, variables, user actions, API data. Inside the box, gears represent logic. On the right, a conveyor belt delivers outputs, return values, UI changes. A warning light on the side of the box is labeled Edge Case Handler, preventing a jam. The visual style should be isometric technical illustration. From vague ideas to rigid blueprints, a pre-code checklist. We have covered the theory. Now, let's look at the execution. Before you type a single prompt into your command center, Chapter 2, To generate code, you should run your idea through the pre-code checklist. This checklist ensures you are not falling into the trap of vague prompting. Treat this as a flight crew pre-check. You don't take off until every box is checked. 1. The atomic goal: is the task small enough? Bad, build a social media app. Good, build the like button functionality for a post. Rule: if you can't describe the inputs and outputs in 1 minute, the task is too big. Break it down. 2. The context verification: does the AI know the stack? Have you reminded the AI you are using Python, React, or AWS? Have you reminded the AI you are a beginner who needs explanations? 3. The Gherkin spec: do you have a given when-then scenario? Is the happy path defined? Is at least one failure path defined? 4. The data contract: do you know what the data looks like? What specific arguments does the function take? What format is the data in? JSON, text, integer? 5. The output format: what do you want back from the AI? Do you want just the code? Do you want the code plus an explanation of the logic? Do you want a separate file for unit tests? Hint: you always want unit tests. We will cover this in phase 3. Putting it all together, that's perfect prompt. By combining these elements, we arrive at a prompt structure that virtually guarantees success. Context: I am building a to-do list app using vanilla JavaScript and local storage. Task: I need a function to add a new task to the list. Intent: Gherkin, given the input field is not empty, when the user clicks add, then create a new task object with a unique ID and save it to the array. Edge case: if the input is empty or just white space, do not create a task and alert the user. Output requirement: please write the JavaScript function and explain how the unique ID is generated. This is intent-driven specification. You are no longer hoping the AI gets it right, you are forcing it to be right. You have shifted from being a passive consumer of code to an active architect of logic. Once you have your specification defined and your code generated, you move to the next phase of the CIVE framework, verification. Because even with the best blueprint, you must still inspect the building. Figure mind map: CIVE phase 2, intent-driven specification, requirement gathering, avoid vague prompts, plan away from keyboard, define success criteria, spec-driven development, Gherkin syntax: a given, context, when, action, then, result, scenario mapping, inputs and outputs, the happy path, edge cases, data contracts, truth tables, pre-code checklist, atomic goal size, context verification, failure paths, output requirements. Chapter 5, CIVE Phase 3, Verification-Driven Development. Sections. Section 5.1, The Trust Gap, Treating AI Code as a Suspicious First Draft. Section 5.2, Rubber Duck Debugging with an AI Partner. Section 5.3, The Build, Delete, Rebuild Loop for Deep Retention. Section 5.4, Test First Methodologies, Writing Failing Tests to Verify AI Success. We have arrived at the most dangerous moment in the software development life cycle. In Chapter 3, you learn to set the context, establishing the persona and environment for your AI partner. In Chapter 4, you mastered intent, meticulously specifying what you want to build before a single line of code was generated. Now, the AI has responded. On your screen sits a block of code. It looks professional. It uses complex keywords. It is syntactically highlighted in beautiful colors. The cursor blinks, waiting for you to copy, paste, and run. Stop. Do not copy that code. Not yet. You are standing at the precipice of the AI death trap we discussed in Chapter 1. The moment you blindly trust the AI's output is the moment you cease to be an engineer and become a liability. In the CIVE framework, Phase 3 is verification. This is the discipline of treating AI-generated code not as a solution, but as a proposal, a highly suspicious first draft that requires your explicit, human audit before it enters your code base. 5.1 The trust gap, treating AI code as a suspicious first draft. To verify code effectively, you must understand the psychology of your AI partner. Large language models, LLMs, are designed to be helpful, not truthful. They are eager to please. If you ask for a function that defies the laws of mathematics, the AI will often attempt to write it rather than correct you. We call this the trust gap. It is the delta between how confident the AI sounds and how accurate the code actually is. Figure, extra detailed AI-ready prompt for AI-generated diagram showing a line graph titled the trust gap. The x-axis is task complexity and the y-axis is confidence. One line represents AI confidence, which remains high and flat at the top. A second line represents actual accuracy, which drops sharply as complexity increases. The gap between the two lines is shaded red and labeled the danger zone, hallucinations. The visual style should be clean, modern technical vector art with a dark background. When an AI generates code, imagine it is a brilliant but overcaffeinated intern. This intern has read every coding book in the library but has zero real-world judgment. They type at lightning speed and speak with absolute authority, even when they are completely wrong. Your job is not to be the typist, your job is to be the senior review. You must scan the code for 3 specific tells of a hallucination. Phantom libraries. Did the AI import a tool that doesn't exist? This happens frequently when an LLM invents a convenient function because it statistically feels like it should exist. Logic loops. Look at the while or for loops. Is there a clear exit condition, or did the AI create a loop that will run forever, crashing your browser? Security amnesia. Did the AI hardcode a password or an API key directly into the script? An AI prioritizes functionality over security unless explicitly told otherwise. Adopting the suspicious first draft mindset changes your physical relationship with the keyboard. You stop rushing to the run button. You lean back. You read. You critique. You only execute the code once you have mentally verified that it does what you asked. 5.2 Rubber duck debugging with an AI partner. In traditional software engineering, rubber duck debugging is a legendary technique. When a programmer is stuck, they explain their code, line by line, to an inanimate rubber duck sitting on their desk. The act of forcing your brain to verbalize the logic often reveals the bug. In Software 3.0, the duck talks back. However, most beginners misuse this dynamic. When they encounter an error, they copy the error message, paste it into the chat, and scream, "Fix this." This is passive debugging. It creates a dependency loop where you cannot solve problems without the tool. Instead, we practice active AI rubber ducking. When code fails, do not ask the AI for the answer immediately. Instead, use the following prompt structure to force yourself to understand the failure. I am getting a key error on line 14. I believe this is because the data dictionary doesn't have the username key I expected. Explain the logic of line 14 to me, and tell me if my hypothesis is correct. By formulating a hypothesis first, you are engaging your logical brain. You are using the AI to verify your intuition, not to replace it. Sometimes, the code works, but you don't understand why. This is equally dangerous. In this scenario, you must force the AI to undergo an interrogation. Highlight the confusing code block and command. Explain this loop to me as if I were 5 years old. Walk through the data transformation at each step. If you cannot explain to a human friend how your application works, you didn't build it, you just assembled it. Verification ensures you own the logic, even if you didn't type the syntax. 5.3 The build, delete, rebuild loop for deep retention. The convenience of AI is its greatest threat to your long-term memory. When you generate code, paste it, and move on, your brain creates no neural pathways for that concept. You obtain the result, but you acquire no skill. To counter this, we introduce the most rigorous exercise in the CIVE framework, the build, delete, rebuild, BDR loop. This technique is designed to transfer knowledge from your short-term working memory into your long-term engineering intuition. It requires courage because it involves destroying your own work. Build, use the AI to help you create a small, atomic feature, e.g., a button that changes color when clicked. Get it working perfectly. Verify the logic. Delete, highlight the code you just verified. Press specific keys, Command+A, then delete. Make the screen empty. Rebuild, retype the logic from memory. You will panic. You will forget the syntax. You will forget if it was on-click or on-click. This struggle is the learning process. When you get stuck, do not ask the AI to write it again. Ask for a hint. I'm rebuilding the button feature. I remember I need an event listener, but I forgot the specific syntax for the click event. Remind me of just that syntax. By typing the solution out manually during the rebuild phase, you are physically encoding the structure of the program into your muscle memory. You are not memorizing the syntax characters, you are internalizing the flow of data. Figure, extra detailed AI-ready prompt for AI-generated diagram of a circular flow chart labeled the BDR retention loop. Top node, AI generation, short-term memory. Arrow points right to, verification, understanding. Arrow points down to, deletion, the void. Arrow points left to, manual reconstruction, long-term encoding. The deletion node should be visually distinct, perhaps bold or warning colored, emphasizing the crucial step of removing the crutch. 5-point for test-first methodologies, writing failing tests to verify AI success. How do you know if the RI's code actually works? You might click around your app and see if it looks right, but vibe checking is not engineering. Professional engineers use test-driven development, TDD. In the context of AI coding, we adapt this into a test-first methodology. The core premise is simple: you define the pass-fail criteria before the AI writes the implementation. If you ask an AI to write a function that calculates a shopping cart total, it will give you code that adds numbers. But will it handle a negative price? Will it handle a tax rate of 0? Will it crash if the cart is empty? Before asking for the solution, ask the AI to help you write a verification test. The prompt pattern. I need to build a Python function that calculates a cart total with tax. First, write a set of 3 assert statements that test edge cases, one for a normal cart, one for an empty cart, and one for a cart with negative prices. I want to see the tests fail before we write the actual function. The AI will generate simple validation logic, like this. Hash the verification layer, the tests. Assert calculate underscore total, 10, 20, tax equals 0.1, equals 33.0 hash normal case. Assert calculate underscore total, tax equals 0.1, equals 0.0 hash empty case. Assert calculate underscore total, dash 5, tax equals 0.1, equals error hash edge case. Now, when you ask the AI to generate the calculate underscore total function, you have a rigorous yardstick to measure it against. You run the code against your tests. If the RI's code fails to handle the negative price, the test will scream at you. This reverses the power dynamic. You are no longer hoping the AI is right, you are proving it. You have defined the constraints of reality, and the AI must operate within them. By mastering verification-driven development, you insulate yourself from the volatility of AI. It doesn't matter if you are using GPT-4, Claude, or a model that hasn't been invented yet. If you can read the draft, verify the logic, and test the outcome, you are the master of the machine. With the logic verified, we are finally ready to make our software real. In the next chapter, we move to the final phase of CIVE, execution. Figure Mind Map Chapter 5, Verification-Driven Development, Mind Map Route, CIVE Phase 3, Verification, the Trust Gap Suspicious First Draft Confidence versus Accuracy Hallucination Tells Phantom Libraries Logic Loop Security Amnesia Active Rubber Ducking Hypothesis Generation Explained to AI Interrogation Proactive vs Passive The BDR Loop Build, AI Assisted, Delete, The Void, Rebuild. Manual recall, muscle memory encoding test first methodology define success before coding edge case. Identification assert statements proving AI logic, figure. Chapter 6, CIVE Phase for Atomic Decomposition and Execution. Sections. Section 6.1, The Spaghetti Code Danger, Why Monolithic Prompts Fail. Section 6.2, Breaking Problems Down, The Strategy of Atomic Tasks. Section 6.3, Isolating Variables, Building Independent Components Step by Step. Section 6.4, Knowing What to Keep, Distinguishing Core Logic from Boilerplate. We have arrived at the final pillar of the CIVE framework. In the previous chapters, you laid the groundwork. You established the context, teaching the AI who it is and what resources it has. You defined your intent, creating a rigorous specification of what needs to be built. You learned the art of verification, ensuring you never blindly trust a machine's output. Now, you are ready to build. This is the phase most beginners try to rush toward. The temptation to skip the planning and simply shout "Build my app" is overwhelming. However, in Software 3.0, execution does not mean asking the AI to do everything at once. Execution is the art of atomic decomposition. It is the discipline of breaking a massive, scary problem into microscopic, manageable tasks that you and the AI can solve together. If context is the soil, intent is the blueprint, and verification is the safety inspector, then execution is the laying of bricks. You cannot pour the entire house out of a bucket, you must lay it brick by brick, ensuring each one is level before moving to the next. 6.1 The Spaghetti Code Danger, Why Monolithic Prompts Fail. The single most common mistake new developers make is that monolithic prompt. A monolithic prompt looks like this: create a Python script that scrapes stock prices, calculates a moving average, saves it to a database, and sends me an email alert if the price drops. To a beginner, this feels efficient. You describe the whole product in one breath. But to an AI, and to the future version of you who has to fix it, this is a disaster waiting to happen. When you ask an LLM to generate 200 lines of code doing 4 different things simultaneously, you dramatically increase the probability of hallucination. The AI loses track of variable names. It forgets to close database connections. It invents libraries that don't exist. The result is what engineers call spaghetti code. It is a tangled mess where everything is connected to everything else. If you try to fix the email alert, you accidentally break the database connection. Figure, extra detailed AI-ready prompt for AI-generated diagram showing a side-by-side comparison. On the left, a monolithic prompt visual depicted as a chaotic, tangled ball of multicolored yarn representing code, with loose ends and knots, labeled the spaghetti trap. On the right, an atomic decomposition visual showing the same colors of yarn neatly wound into separate, distinct spools arranged in a straight line, labeled atomic execution. The style should be clean, isometric vector art with soft lighting. The danger of the monolithic prompt is that it hides complexity. When the code fails, and it will fail, you won't know which part is broken. Did the scraper fail? Was the calculation wrong? Did the database lock up? Because you generated it all at once, you have to debug it all at once. That is a nightmare even for senior engineers. In Phase 4 of CIVE, we reject the monolith. We refuse to ask the AI for the whole thing. Instead, we act as the project manager, feeding the AI one slice of the problem at a time. 6.2 Breaking Problems Down, The Strategy of Atomic Tasks. The antidote to spaghetti code is atomic decomposition. In physics, an atom is the smallest unit of matter that retains the properties of an element. In software, an atomic task is the smallest unit of work that can be executed and verified independently. Your job as an AI native developer is to take your intent, from Chapter 4, and slice it into atoms. Let's revisit the stock price example. Instead of one giant prompt, we break it down into 4 atomic interactions. Atom A, write a function that only fetches the current price of a stock. Verify it prints the price. Atom B, write a function that takes a list of numbers and calculates the moving average. Verify the math is correct. Atom C, write a script that connects to a database and saves a single record. Verify the data appears in the table. Atom D, write a function that sends a test email. Verify the email arrives. Only after these four atoms are verified do you ask the AI to combine them. This strategy changes your psychological relationship with the code. You are no longer praying that a black box works. You are assembling a machine from parts you have already tested. When you work atomically, errors are isolated. If atom A fails, you know exactly where to look. You don't have to check the database or the email settings. You only have to fix the fetch function. This is how you maintain control. You constrain the AI's creative freedom to a single, verifiable box. You force the LLM to focus all its processing power on one specific task, which drastically increases the quality of the code it generates. 6.3 Isolating variables, building independent components step by step. Once you have decomposed your problem, you must execute the solution in a specific order. This is called isolation of variables. Imagine you are building a car. You wouldn't install the engine, the wheels, and the radio simultaneously. You would build the chassis, then mount the engine, then test if the engine starts. In programming, we build from the inside out. We start with the core data, then add the logic, and finally add the user interface. Let's look at a practical workflow for a beginner building a simple tip calculator web app. Step 1. The logic layer, no UI. First, ask the AI to write a Python or JavaScript function that takes a bill amount and a tip percentage, and returns the total. Run this in your terminal. Does 100 plus 20% equal 120? Yes. The logic is isolated and verified. Step 2. The structure layer, HTML. Next, ask the AI to generate the HTML for the input fields and a button. Don't ask for styling yet. Just get the elements on the screen. Step 3. The integration layer. Now, ask the AI to connect your Step 1 logic to your Step 2 HTML. When the button is clicked, run the math. Step 4. The presentation layer, CSS. Finally, ask the AI to make it look pretty. Figure, extra detailed AI-ready prompt for AI-generated diagram showing a layer cake, a visualization of software development. The bottom layer is labeled data and logic, colored deep blue, the middle layer is integration, colored purple, and the top layer is presentation UI, colored bright teal. An arrow labeled execution flow points upward from the bottom layer to the top, indicating the order of building. High-tech, blueprint aesthetic. If you try to do Step 4 presentation before Step 1 logic, you will get distracted by how the button looks rather than if it works. By isolating variables, you ensure that bugs are easy to find. If the total is wrong, you know the error is in the logic layer. If the button is ugly, the error is in the presentation layer. They never mix. This is the secret to moving fast. Slow down. Build one verified layer at a time. 6 point for knowing what to keep, distinguishing core logic from boilerplate. As you execute these atomic tasks, you will notice a pattern in what the AI produces. Some code is generic. It looks the same in every application. Setting up a server, centering a div on a web page, or importing standard libraries. This is called boilerplate. Other code is specific to your problem. The formula you use to rank search results, the specific way you handle user data, or the rules for your game. This is core logic. To execute effectively, you must learn what to delegate completely and what to scrutinize intensely. Delegate the boilerplate. You do not need to memorize how to configure a Webpack server or how to write the CSS to make a grid responsive. The AI is perfect at this. It has seen millions of examples. Let the AI generate this code rapidly. If it works, move on. Own the core logic. You must understand the business logic. If you are building a mortgage calculator, you cannot blindly accept the AI's formula for compound interest. You need to read that specific line of code. You need to verify it against a real calculator. If you treat core logic as boilerplate, you enter the death trap. You become a developer who builds apps that look great but calculate wrong. In the execution phase, your attention is your most valuable currency. Do not spend it checking if the AI imported the right library. The compiler will tell you if it didn't. Spend it checking if the AI understood the intent of your algorithm. The CIVE framework, context, intent, verification, execution, is your loop. You will cycle through these for phases hundreds of times per project. For every atomic task, you set the context, define the intent, execute the prompt, and verify the result. Then you move to the next atom. You are no longer just typing code. You are assembling a system. Figure mind map, the CIVE phase for execution strategy, root, CIVE phase for execution, atomic decomposition definition, breaking big problems into indivisible units, goal, isolate errors, enable verification, metaphor, laying bricks versus pouring a house, the spaghetti danger monolithic prompts, asking for everything at once, risks hallucinations context loss unfixable bugs isolation of variables step 1, logic layer, the math, step 2, structure layer, the skeleton, step 3, integration layer, the connections, step 4, presentation layer, the look, the 80/20th attention rule delegate, boilerplate CSS config, scrutinize, core logic algorithms data safety. Chapter 7, the computer science fundamentals you cannot skip. Sections. Section 7.1, Data Structures Explained, Arrays, Dictionaries, and JSON Payloads. Section 7.2, Algorithmic Logic, Conditionals, Loops, and Control Flow. Section 7.3, Understanding State, How Machines Remember and Forget Information. Section 7.4, The 80/20th Rule, Focus Areas for the High-Level Orchestrator. We have spent the last few chapters discussing process. We covered how to set up your environment, how to prompt for intent, and how to break problems down. But now, we must address the elephant in the room. There is a pervasive myth in the no-code and low-code communities that implies you never need to understand how computers actually think. The sales pitch is seductive, just talk to the AI, and it will handle the rest. This is dangerous half-truth. While you no longer need to memorize the syntax for how to reverse a string in JavaScript or how to allocate memory in C++, you absolutely must understand the concepts behind those actions. If you do not understand the building blocks of logic, you cannot verify if the AI is building a cathedral or a house of cards. You are the architect, the AI is the contractor. The contractor can lay the bricks perfectly, but if you don't understand the physics of load-bearing walls, the building will collapse. In this chapter, we are going to strip away the academic fluff found in university textbooks. We will focus strictly on the big three concepts that govern 90% of the software you will build: data structures, algorithmic logic, and state. 7.1 Data Structures Explained, Arrays, Dictionaries, and JSON Payloads. Software is effectively just two things: information, data, and doing things with that information, algorithms. If you don't organize your information correctly, you can't do anything with it. Imagine a library where every book is thrown into a giant pile in the middle of the room. It contains the same information as an organized library, but it is useless because you cannot retrieve what you need. Data structures are the shelves. For the AI native developer, you only need to master 3 specific structures to build almost any modern application. The array, the list. The simplest way to organize data is a list. In computer science, we call this an array, or a list, depending on the language. Think of an array as a single column in a spreadsheet. It has a specific order. There is a first item, a second item, and a last item. When you are prompting an AI, you use arrays when the order matters or when you have a collection of similar items. Real-world analogy: a shopping list, a playlist of songs, or a queue of people waiting for tickets. The AI prompt tip: when you want the AI to process items one by one, ask it to iterate through the array. Hash a simple list of users. Users equals Alice, Bob, Charlie, Diana. The dictionary: key-value pairs. Sometimes, order doesn't matter, but labels do. Imagine you want to find a specific person's phone number. You don't want to look through a random list, you want to look up their name, the key, and get their number, the value. This is a dictionary, also called a hash map or object. Real-world analogy, a physical dictionary, word-definition, a contact list, name-phone number, or a user profile, field-data. The AI prompt tip, use dictionaries when you need to label data. Create a user object that stores their email, name, and age. Hash a dictionary representing one user. User_profile equals name, Alice. Email, alice@example.com. Role, admin. JSON, the lingua franca of AI. This is the most critical concept for you to learn. JSON, JavaScript Object Notation, is the standard format for moving data between servers, web browsers, and AI models. When you ask ChatGPT to analyze a file, or when your app fetches weather data from the internet, it is almost certainly doing so using JSON. JSON is essentially a mix of arrays and dictionaries nested inside each other. If you understand the structure of JSON, you can debug almost any modern application. Figure, a clean, high-contrast diagram showing a JSON object on the left and a visual tree representation on the right. The JSON contains a user key, which branches into name, string, and orders an array of items. Arrows connect the code syntax to the visual blocks to show hierarchy. When the AI writes code that fails, 50% of the time it is because the shape of the data was wrong, it tried to read a list like a dictionary. 7.2 Algorithmic logic, conditionals, loops, and control flow. Once your data is organized, you need to apply logic to it. You don't need to know how to write complex sorting algorithms from scratch, the AI does that, but you must understand control flow. Control flow is the traffic direction of your software. It decides which lines of code run and which are skipped. Conditionals, if-else. This is the brain of your software. It allows the program to make decisions based on the state of the data. Concept, if this thing is true, then do this action, else do that action. The beginner trap, beginners often forget to cover the else, the edge cases. Verification, when the AI writes an if statement, ask yourself, what happens if the opposite is true? Hash the logic is simple, but vital. If user underscore is underscore logged underscore in, show underscore dashboard. Else, redirect underscore to underscore login. Loops, for while. Computers are excellent at doing boring tasks repeatedly without making mistakes. Loops allow you to run the same logic over a list of items. For loops, used when you know how many times to repeat, e.g., send an email to every user in this list. While loops, used when you want to keep going until a condition changes, e.g., keep trying to connect to the server until it responds. The danger with AI-generated loops is the infinite loop. If the AI writes a while loop but forgets to include a way for the loop to stop, your application will freeze and crash. Always verify the exit condition of a loop. 7.3 Understanding state, how machines remember and forget. This is the concept that trips up self-taught developers more than any other. State is the current status of your application at a specific moment in time. It is the snapshot of all your variables, user inputs, and data. Imagine you are playing a video game. The state includes 1. Your current health. 2. Your position on the map. 3. The items in your inventory. If you turn off the console without saving, that state is lost. Computer memory works the same way. The stateless web. Here is the hard truth about web development: the internet is largely stateless. When you visit a website, the server sends you the page and immediately forgets who you are. To make an app interactive, like keeping you logged in, we have to artificially manage state using databases, browser cookies, or local storage. When you ask an AI to build a shopping cart, it might write code that visually shows a cart. But if you refresh the page and the cart empties, you have a state management problem. The AI built the interface, the view, but it didn't persist the data, the state. Figure, a split diagram. Top half shows volatile state, RAM, represented as a whiteboard that gets erased when the power goes out. Bottom half shows persistent state, database, represented as a filing cabinet that retains data after a reboot. Icons represent a user refreshing a browser window. Key takeaway for prompting: never just ask for a feature, ask about the life cycle of the data. Asterisk bad prompt, add a dark mode toggle. Asterisk good prompt, add a dark mode toggle, and save the user's preference in local storage so it remembers their choice when they return. 7 point for the 80/20th rule, focus areas for the high-level orchestrator. Computer science is a massive field. You could spend 4 years studying compiler theory, binary arithmetic, and memory pointers. In the age of AI, you can safely skip 80% of that theory. The AI is better at bit shifting and memory allocation than you will ever be. Your job is not to be the mechanic tinkering with the engine valves, your job is to be the driver navigating the road. Here is your safe to skip versus must know list. Concept status: why? The orchestrator's mindset. As you move into the tutorials in the next section of this book, I want you to change how you look at code blocks. Do not read the code character by character. Do not stress if you miss a semicolon. Instead, look for the flow. 1. Input. What data is coming in? Is it a JSON object? An array? 2. Transformation. What logic is changing that data? Is there a loop? An if statement. 3. Output. What is the new state? Did we save to a database? Did we update the screen? If you can track the data flow, you are a programmer. Everything else is just syntax, and syntax is now a commodity. You have the theory. You have the environment. You have the framework. In the next chapter, we stop talking and start building. It is time to learn how to read the code the AI writes, not as a student, but as an editor. Figure Mind Map Chapter 7, Computer Science Fundamentals, Central Node, CS Fundamentals for AI Coding, Branch 1, Data Structures, Subnode, Arrays, Lists, Ordered Items, Iterate, Subnode, Dictionaries, Key Value, Labels, Lookups, Subnode, JSON, Universal Format, Nested Structures, Branch 2, Algorithmic Logic, Subnode, Control Flow, Traffic Direction, Subnode, Conditionals, If, Else, Decision Making, Subnode, Loops, For While, Repetition, Exit Conditions, Branch 3. Understanding State, Subnode, Definition, Snapshot in Time, Subnode, Volatile versus Persistent, RAM versus Database, Subnode, Stateless Web, Cookies, Local Storage, Branch 4, the 80/20th Rule, Subnode, Skip, Syntax, Memory Allocation, Binary, Subnode, Focus, Data Flow, API Logic, Debugging, Subnode, Goal, be the orchestrator, not the mechanic. Chapter 8, Moving from Writer to Editor. Sections. Section 8.1, The Shift in Daily Responsibilities, Reading Code is the New Writing. Section 8.2, Auditing AI Output for Security Vulnerabilities and Logic Flaws. Section 8.3, Refactoring with Assistance, Cleaning up Messy Machine Output. Section 8.4, Tracing Execution, How to Mentally Run Code to Spot Errors. For decades, the archetype of a computer programmer was a frantic typist. We imagine the hacker in a movie, fingers flying across a mechanical keyboard, green text cascading down the screen as they'd write the virus or the firewall in real time. In the era of Software 1.0, this was somewhat true. Mastery was defined by how quickly you could recall syntax and how fast you could type valid code. If you stopped typing, the software stopped being built. In Software 3.0, you are no longer the typist. You are the editor-in-chief. This is a fundamental shift in your relationship with the machine. When you use the CIVE framework, the AI does the heavy lifting of generation. It produces the raw material, the loops, the function definitions, the CSS styles, at a speed no human can match. Your job is not to compete with that speed. Your job is to slow it down. As an AI native developer, your value is no longer measured by lines of code written per hour. It is measured by your ability to read, audit, critique, and refine the code the AI produces. You are moving from the role of the author, who struggles with a blank page, to the editor, who polishes a rough draft into a masterpiece. 8.1 The shift in daily responsibilities. Reading code is the new writing. There is an old adage in software engineering: code is read 10 times more often than it is written. In the age of AI, this ratio is shifting closer to 100 to 1. When you ask an LLM to generate a function, you have skipped the writing phase entirely. However, you have immediately inherited the responsibility of the reading phase. The AI does not know why the code works, it only knows statistically probable patterns. It is up to you to confirm that the pattern fits your specific context. This transition can feel uncomfortable for beginners. Reading code is cognitively demanding. When you write code yourself, you build a mental map of the logic as you go. When you read AI-generated code, you are dropped into the middle of someone else's thought process, or in this case, a machine's statistical prediction. To be a successful editor, you must abandon the habit of skimming. When we read English text, we skim. We look for keywords and infer meaning from context. If you skim code, you will miss bugs. A single misplaced character, A instead of A equals, or A instead of A equals, can invert the entire logic of your application. Figure, a split-screen illustration contrasting skimming versus tracing. On the left, a blurry eye scans a block of text rapidly. On the right, a magnifying glass focuses intensely on a single line of code if user_balance, transfer_amount, with annotations showing the reader checking specific variable values. The style should be clean, technical line art. You must adopt the mindset of a contract lawyer. You are looking for loopholes. You are looking for the exact moment the logic fails. You are not reading for vibes, you are reading for truth. 8.2 Auditing AI output for security vulnerabilities and logic flaws. The greatest weakness of generative AI is that it is a people pleaser. If you ask an AI to fix a bug, and the easiest way to fix that bug creates a massive security hole, the AI will often choose the security hole. It prioritizes satisfying your immediate prompt over maintaining long-term system integrity. As the editor, you must constantly audit for the happy path bias. The happy path is a scenario where everything goes right, the user enters the correct password, the database is online, and the internet connection is stable. AI loves the happy path. Real software lives in the sad path. Consider a scenario where you ask the AI to write a Python script to connect to a database. The AI might happily generate this. Warning, this is an example of bad practice commonly generated by AI. Import OS. Def connect _to database. The AI hard-coded the password directly into the script. db_password equals my_secret_password_123. db_URL equals fpostgres//user db_password at localhost 5432 chemydb. Print f's connecting to edb_URL. Return db_URL. If you copy this code, you have just committed a cardinal sin of security. You have hard-coded credentials. If you upload this code to GitHub, hackers will scrape it in seconds. The AI didn't do this to be malicious. It did it because it is the simplest way to make the code run right now. As the editor, your job is to spot this. You must intervene and say, no, we do not hardcode secrets. You would then refactor the code to use environment variables, a concept we touched on during environment setup. The editor's correction. Import OS. Def connect _to database. Fetching the password from the secure environment. db_password equals os.getenv db_password. If not db_password. Raise value error, database password not found in environment variables. db_URL equals fpostgres//user db_password at localhost 5432 chemydb. Return db_URL. Notice the difference. The editor's version anticipates failure, if not db_password, and protects the secret. The AI provides the raw material, you provide the safety rails. 8.3 Refactoring with assistance, cleaning up messy machine output. AI code often works, but that doesn't mean it is good. Large language models have a tendency to write spaghetti code. This is code that is tangled, repetitive, and difficult to modify later. It might write a function that is 100 lines long, doing 5 different things at once. In Software 1.0, beginners were often afraid to change code once it worked. They treated it like a house of cards. If they touched it, it would collapse. In Software 3.0, code is cheap. You should be ruthless about deleting and improving it. This process is called refactoring. Refactoring is the art of changing the structure of code without changing its behavior. It is cleaning up the kitchen after you've cooked the meal. You can actually use the AI to help you do this, acting as a senior editor to your junior writer. Once the AI generates a solution that works, your next prompt should rarely be, "Okay, what's next?" Instead, your prompt should be, "This code works, but it is messy. Refactor this to be more readable." Break the large function into 3 smaller functions and add comments explaining the logic. Let's look at a practical example. The AI might generate a nested loop that is hard to read. # messy AI generation. Def process_orders, orders. For order in orders. If order, status, equals, paid. If order, total, greater than 100. Print, F processing expensive order, order, ID. # complex logic. Else? Print, F processing standard order, order, ID. # complex logic. This is a nested logic, and it places a heavy cognitive load on the reader. As the editor, you can demand a guard clause pattern to flatten the structure. # refactored by the editor with AI assistance. Def process_orders, orders. For order in orders. # guard clause, handle the negative case first and exit early. If order, status, equals, paid. Continue. # now the rest of the function is flat and easier to read. If order, total, greater than 100. Process_expensive_order, order. Else? Process_standard_order, order. The logic is identical. But the second version is professional. It is modular. It is easier to debug. By forcing the AI to refactor its own work, you learn the difference between code that merely runs and code that lasts. 8 Point for tracing execution, how to mentally run code to spot errors. The ultimate skill of the editor is mental tracing. This is the ability to look at a block of code and simulate the computer's behavior in your mind, line by line. You are essentially becoming a human compiler. Beginners often skip this. They see a loop and assume they know what it does. Then they run the program, get an error, and blindly ask the AI to fix it. This creates a dependency loop where you never truly understand the system's state. To practice mental tracing, you need a physical tool, a piece of paper and a pen. We use a technique called a trace table. When you are auditing a complex piece of AI logic, draw a table with columns for every variable in the code. Figure, a close-up photo of a handwritten trace tables on a notepad. The columns are labeled I, current_sum, and output. Rows show the changing values, row 1, I equals 0, current_sum equals 0. Row 2, I equals 1, current_sum equals 5. Row 3, I equals 2, current_sum equals 12. A pen rests on the paper, emphasizing the manual nature of this process. Let's trace a simple loop that calculates a sum. Numbers equals 2, 5, 8. Total equals 0. For num in numbers, total equals total plus num. Print total. Don't just run this. Trace it. Initialization, total is 0. Numbers is 2, 5, 8. Iteration 1, num becomes 2. Total becomes 0 plus 2 is equal to 2. Screen prints 2. Iteration 2, num becomes 5. Total becomes 2 plus 5 is equal to 7. Screen prints 7. Iteration 3, num becomes 8. Total becomes 7 plus 8 is equal to 15. Screen prints 15. Termination, no more numbers. The loop ends. This seems trivial with simple math. But what if the AI wrote a loop that modifies the list while it is iterating over it? That is a common source of infinite loops or crashes. If you can trace the variables on paper, you will spot the logic flaw before you ever press run. This is the discipline that separates the vibe coder from the software engineer. The vibe coder hopes it works. The engineer knows it works because they have already run the code in their mind. As you move forward to building your portfolio, remember this shift. You are not just a prompt engineer. You are the quality control department. You are the security auditor. You are the editor. The AI provides the raw intelligence, but you provide the wisdom. Figure mind map, Chapter 8, moving from writer to editor, root, Chapter 8, the editor mindset, 8.1 the shift, writing versus reading, marker, old, 80% typing, marker, new, 80% auditing, the danger of skimming, marker, inverting logic, marker, missing symbols, 8.2 auditing AI, the yes man problem, marker, AI prioritizes satisfaction over safety, the happy path bias, marker, assuming perfect inputs, security risks, marker, hard-coded secrets, marker, SQL injection, 8.3. Refactoring, spaghetti code, marker, messy AI output, refactoring definition, marker, changing structure, not behavior, techniques, marker, guard clauses, marker, atomic functions, 8. For mental tracing, human compiler, marker, running code in your head, trace tables, marker, tracking variables manually, goal, marker, certainty over hope, / figure. Chapter 9, Safety Nets, Version Control and Rollbacks. Sections. Section 9.1, GIT Fundamentals, Your Insurance Policy Against Bad Prompts. Section 9.2, Creating Prefix Checkpoints Before Applying AI Suggestions. Section 9.3, Branching Strategies for Experimentation and Refactoring. Section 9.4, Reverting Catastrophes, Recovering from Destructive AI Hallucinations. Imagine you are playing a difficult video game. You have spent 3 hours fighting through a dungeon, collecting rare items, and leveling up your character. You finally reach the door to the boss room. What is the very first thing you do? You save the game. You do this because you know there is a high probability of failure ahead. If the boss defeats you, or if the game crashes, you do not want to start over from the beginning of the dungeon. You want to respawn right at that door, with all your progress intact. In Software 1.0, manual coding, developers learned to save the game using a tool called GIT. It was important then, but in the era of Software 3.0, it is a matter of survival. When you code with AI, you are moving at warp speed. You can generate hundreds of lines of code in seconds. You can refactor an entire database schema with a single prompt. This speed is exhilarating, but it is also volatile. One bad prompt, one hallucinated import, or one misunderstanding of your intent can turn a perfectly working application into a smoking crater of error messages. If you rely on undo, Ctrl+Z, you are gambling. AI changes too many files at once for a simple undo command to track effectively. This chapter introduces your safety net. We will move beyond treating code as a fragile text file and start treating it as a history of snapshots. By mastering version control, you gain the freedom to experiment fearlessly with AI, knowing you can always teleport back to a time when everything worked perfectly. 9.1 GIT Fundamentals, your insurance policy against bad prompts. GIT is often taught to beginners as a tool for collaboration, a way to share code with a team. While true, that perspective is irrelevant to you right now. For the AI native developer, GIT is a time machine. At its core, GIT allows you to take a snapshot of your entire project folder at a specific moment in time. Unlike saving a Word document, where the new version overwrites the old one, GIT keeps every snapshot you have ever taken. You can browse through them, compare them, and most importantly, revert to them. To use this effectively, you must understand 3 states of being in GIT. Do not memorize the command line syntax yet, understand the logic first. *** the working directory ***, this is the code you are currently looking at in your editor, VS Code or cursor. It is volatile. If you delete a file here, it is gone. ***, the staging area ***, this is a pre-save holding zone. You pick specific changes you want to keep and place them here. Think of it as putting items into a box before taping it shut. ***, the repository, commit ***, this is the sealed box. Once you commit the changes, they are permanently recorded in the timeline. Figure, extra detailed AI-ready prompt for AI-generated diagram showing the 3 stages of GIT. The visual should look like a horizontal flow. Left, a chaotic desk labeled working directory or with loose papers. Middle, a neat cardboard box labeled staging area where some papers are being placed. Right, a secure, locked vault labeled repository containing a stack of sealed boxes. Arrows indicate the flow from desk to box to vault. Style, isometric, clean vector art, soft blue and gray color palette. When working with an LLM, your workflow changes from write-save to prompt-verify-commit. If you ask the AI to build a login form and it works, you commit that code immediately. That is your save point. If you then ask the AI to style the form and it breaks the login functionality, you do not panic. You simply discard the changes in your working directory and reset to the last commit. This psychological shift is massive. It transforms AI from a risky chaotic element into a controlled tool. You are no longer afraid of breaking things because you have an insurance policy. 9.2 Creating prefix checkpoints before applying AI suggestions. The most common tragedy for a junior developer using AI looks like this. The code works, but there is one small bug. The developer pastes the error into the AI. The AI suggests a massive rewrite of 3 files. The developer pastes the new code. The original bug is gone, but now the entire application fails to start. The developer realizes they can't remember what the old code looked like. This is the AI death trap in action. To avoid this, you must adopt the discipline of the prefix checkpoint. Before you ever paste a solution from an AI that claims to fix a bug or refactor code, you must secure the current state, even if that state is broken. It seems counterintuitive to save broken code. You might think, why would I save a version that has a bug? You save it because it is a known bug. It is a stable state of brokenness. The RA's fix might introduce unknown bugs that are far worse. Here is the golden rule of AI execution: never paste AI code into a dirty working directory. A dirty directory means you have modified files that haven't been committed. If you paste AI code on top of uncommitted human edits, you are mixing variables. If things go wrong, you cannot disentangle your changes from the RA's changes. The safe workflow. Status check, you identify a bug. Commit, you run git commit m save point, app runs but login button is misaligned. Prompt, you ask the AI for the fix. Apply, you paste the RA's code. Verify, does it work? Yes, commit the new changes, git commit m fix, aligned login button. No, revert to the save point, git restore. By following this loop, you turn software development into a ratchet mechanism. You can only move forward or stay put, you never slip backward into chaos. 9.3 Branching Strategies for Experimentation and Refactoring. Sometimes, you want to ask the AI to do something bold. Perhaps you want to switch your database from SQLite to PostgreSQL. Or maybe you want to ask the AI, rewrite this entire CSS structure to use Tailwind instead of Bootstrap. These are high-risk operations. If the AI hallucinates halfway through, your project will be in a state of unrecoverable surgery, gut spilling out, nothing connected, red error lines everywhere. For these moments, you need branches. In our video game analogy, a commit is a save point. A branch is an alternate timeline. When you create a branch, you are splitting the universe. You have the main timeline where your code works, mostly. You create a new timeline called experimental redesign. You can let the AI run wild in this new timeline. It can delete files, rename folders, and rewrite logic. If the AI succeeds, and the new design is brilliant, you merge that timeline back into the main one. If the AI fails, and the code becomes a mess, you simply delete the timeline. You switch back to main, and it is as if the experiment never happened. How to prompt for this? When you are about to start a large AI task, explicitly tell the AI you are branching. I am creating a new Git branch called refactorauth. I want you to guide me through switching from local authentication to OAuth 2. If we hit a dead end, I need to be able to abandon this branch without affecting my main application. This provides context to the AI. It understands that it has permission to be destructive because you are working in a sandbox. Hash the command to create a parallel universe. Git checkout b try new feature. Hash. You apply AI changes here. Hash if it works. Git checkout main. Git merge try new feature. Hash if it fails. Git checkout main. Git branch a d try new feature. As an AI native developer, you should be creating branches constantly. Treat them as disposable scratchpads. Never let an AI refactor your main code base directly. Always force it to prove itself in a branch first. 9 Point for reverting catastrophes, recovering from destructive AI hallucinations. Despite your best efforts, there will be times when you commit bad code. You might be tired, or the AI might be incredibly convincing, and you click commit before you realize the login page is now blank. In the past, this induced panic. Developers would frantically try to fix forward, asking the AI to patch the error, which creates a new error, leading to a downward spiral of spaghetti code. With version control, you do not fix forward. You roll back. There are two primary ways to handle this, and you need to know which one to use so you don't erase history you actually wanted to keep. The soft undo, Git revert. Imagine you built a feature, committed it, and then realized 2 days later that it introduced a security flaw. You don't want to erase the last 2 days of work, you just want to cancel out that specific mistake. Git revert creates a new commit that does the exact opposite of the bad commit. If the bad commit added a line, the revert commit removes it. This preserves your history while negating the error. The hard reset, the nuclear option. This is for when you have gone down a rabbit hole with the AI for the last hour, made 3 or 4 commits, and realized the entire direction is wrong. You want to wipe it all away and go back to how the world looked at 9 a.m. Git reset hard is powerful. It grabs the timeline and drags it back to a specific point, erasing everything that happened after it. Figure, extra detailed AI-ready prompt for AI-generated diagram comparing Git revert vs Git reset. Top half shows Git revert, a timeline of blocks ABC. A new block D is added that cancels out B, resulting in ABCD, safe. Bottom half shows Git reset, timeline ABC. The hand of God cuts the timeline after A, and B and C vanish into dust, leaving only A, destructive. Style, conceptual, high contrast, using red for destruction and green for addition. The AI recovery prompt. If you are stuck in a bad state and don't know the Git commands, you can use the AI to help you escape, but you must use a context-first prompt, as learned in Chapter 4. Prompt: I have made several bad commits and my code is broken. I want to return to the state of the code as it was yesterday. Please explain the difference between Git reset and Git revert in this context, and give me the exact commands to view my history and jump back to a safe point. By mastering these rollbacks, you remove the fear of breaking your computer. You can drive the car as fast as you want, because you know exactly how to teleport back to the garage if you crash. You are no longer just coding, you are managing a timeline of evolution. In the next chapter, we will take this confidence and apply it to building your first real-world application, vibe coding your way to a portfolio piece with the safety net securely underneath you. Figure Mind Map, Chapter 9, Safety Nets, Central Node, Version Control and Safety Nets, Node, Why Git? Child, Time Machine vs Saving, Child, Undo isn't enough for AI, Child, Freedom to Experiment, Node, Core Concepts, Child, Working Directory, Volatile, Child, Staging, Preparation, Child, Commit, Snapshot Save Point, Node, The Workflow, Child, Prefix Checkpoint, Subchild, Commit before pasting AI code, Subchild, Never paste into dirty directory, Child, Verification Loop, Subchild, Prompt dash, Verify dash Commit, Node, Branching, Child, Parallel Universes, Child, Use for high risk. AI refactors, Child, Merge if successful, Delete if failed, Node, Recovery, Child, Revert, Soft Undo, Inverse, Child, Reset, Nuclear, Time Travel, Child, Don't fix forward, rollback instead. Chapter 10, Blueprint to Reality, Building Your First App. Sections. Section 10.1, Project Setup, Fetching Live Data with Python and APIs. Section 10.2, Data Processing, Cleaning and Preparing Datasets with Pandas. Section 10.3, Visualization, Using Matplotlib to Render Insights. Section 10.4, Handling Errors, Real-Time Debugging of a Live Application. We have spent the previous chapters building your mental operating system. You understand the CIVE framework. You know how to engineer context, define intent, and verify the output. You understand the safety net of version control. Now, it is time to take the training wheels off. Theory is comfortable. It is safe. But software engineering is a contact sport. You cannot learn to swim by reading about fluid dynamics. Eventually, you have to get wet. In this chapter, we are going to build a real, functioning application from scratch. We will not be building a Hello World app. We are going to build a financial data visualizer. This application will connect to the live internet, fetch real-time currency exchange data, clean that data using professional-grade tools, and generate a visual chart. It is a classic ETL pipeline: extract, transform, load, the bread and butter of the professional developer. You are about to experience the vibe coding phase we discussed in the introduction, but with a crucial difference: you are not blindly copying code. You are orchestrating it using the CIVE framework. 10.1 Project Setup, Fetching Live Data with Python and APIs. Before we write a single line of code, we must establish our context. In the old world, Software 1.0, you would need to memorize how the Python requests library works. In Software 3.0, your job is to understand the concept of an API, Application Programming Interface. Think of an API as a menu in a restaurant. You, the app, cannot go into the kitchen, the server, and cook the food yourself. Instead, you look at the menu, the API documentation, tell the waiter what you want, the request, and the waiter brings it to you with the response. For this project, we need a library that acts as our waiter. The context-first prompt: open your AI editor, Cursor, Copilot, or ChatGPT, and set the stage. Do not ask for code yet. User: I am a beginner building a Python script to fetch exchange rates. Explain how the requests library allows Python to talk to web APIs, and what a JSON response typically looks like. Once the AI explains this, you have verified that it understands the domain. Now, we move to intent. We need to fetch data. For this tutorial, we will simulate fetching data from a standard currency API. We want to see the exchange rates between the US dollar, USD, and the euro, EUR, over time. The execution prompt. User, write a Python function called fetch_exchange_rates. It should use the requests library to get data from a sample API URL. For now, let's pretend the URL is the function should return the JSON data. Include error handling if the website is down. The AI will generate code similar to this. Import requests. Def fetch_exchange_rates. URL equals try. Response equals requests.get URL. Hash check if the request was successful, status code 200. Response.raise_for_status. Return response.json. Accept requests.exceptions.requestException as E. Print F error fetching data E. Return none. Hash test the function. Data equals fetch_exchange_rates. Print data. Stop. Do not assume this works. Apply verification. Run the script. If the URL is valid, you will see a messy block of text in your terminal. It looks like a dictionary, base, USD, rates, EUR, 0.85, GBP, 0.75. This is JSON. It is the raw ingredient of the modern web. If you see this, you have successfully connected your computer to the outside world. Figure, a clean, minimalist diagram showing the flow of data. On the left, a laptop icon labeled your Python script. An arrow labeled request, get, who points to a cloud icon labeled API server. A return arrow labeled response, JSON, points back to the laptop. The JSON arrow is stylized to look like a package being delivered. High contrast, technical schematics style. 10.2 Data processing, cleaning and preparing datasets with pandas. Raw data is rarely useful. It is often nested, messy, or formatted incorrectly for humans. In professional software development, this is where Pandas comes in. Pandas is essentially Microsoft Excel for Python, but without the graphical interface. It allows you to manipulate millions of rows of data in milliseconds. Your goal, intent, is to take that raw JSON dictionary and turn it into a structured table, called a data frame in Python, so we can analyze it. The atomic decomposition, we are not asking the AI to finish the app. We are asking it to perform the next atomic task, transformation. The prompt. User, I have a JSON object containing exchange rates. I need to convert the rates section of this JSON into a pandas data frame. The data frame should have two columns, currency and rate. Show me how to import pandas and perform this conversion. The AI will guide you to install pandas, pip install pandas, and then provide the implementation. Import pandas as PD. Def process_data, JSON_data. If JSON_data is none, return none. Hash extract the rates dictionary. Rates_dict equals JSON_data.get, rates. Hash convert to data frame. df equals PD data frame, list, rates_dict.items, column sad smiley a currency, rate. Hash let's sort it by rate to make it readable. df equals df.sort_values, by equals rate, ascending equals false. Return df. The verification step, update your script to call this new function. Raw_data equals fetch_exchange_rates. Clean_df equals process_data, raw_data. Print, clean_df.head. When you run this, you should no longer see the messy JSON text. You should see a neat, aligned table in your terminal. Currency rate. 45 VND 23,000.0. 12 Japanese yen 110.0. If you see this table, you have successfully performed data munging. You have taken raw chaos and turned it into structured order. This is 80% of what professional data engineers do every day. 10.3 Visualization, using Matplotlib to render insights. A table of numbers is better than JSON, but a chart is better than a table. We will use a library called Matplotlib. It is the standard plotting library for Python. It can be intimidating because it has thousands of settings, but this is where AI thrives. You do not need to memorize how to rotate x-axis labels, you just need to describe the visual you want. The intent specification, be specific. If you just say, chart this, the AI will guess. The prompt. User, I want to create a bar chart of the top 10 most valuable currencies from my data frame. Use Matplotlib. The x-axis should be the currency codes, and the y-axis should be the exchange rate. Make the bars blue. Add a titled Top 10 Exchange Rates versus USD. Rotate the x-axis labels so they don't overlap. The AI acts as your front-end designer. Import matplotlib.pyplot as PLT. Def visualize _ data, df. If df is none or df.empty. Print, no data to visualize. Return. Hash get the top 10. Top _ 10 equals df.head, 10. Hash create the plot. plt.figure, figsize sad smiley 10, 6. plt.bar, top _ 10, currency, top _ 10, rate, color equals sky blue. Hash add labels. plt.title, top 10 exchange rates versus USD. plt.xlabel, currency. plt.ilabel, exchange rate. plt.xticks, rotation equals 45. Hash display the chart. plt.tight _ layout. plt.show. The execution, add this function to the bottom of your script and run it. A window should pop up on your screen. You should see a professional-looking bar chart. Take a moment to appreciate this. In less than 30 minutes, you have built a pipeline that travels across the internet, processes data, and renders a visual report. You did not memorize the syntax for plt.bar or pd data frame. You used logic to direct the AI to build the components you needed. Figure, a detailed illustration showing the computer screen with the generated bar chart. The chart has blue bars, clear axis labels, and a title. Superimposed over the screen is a semi-transparent blueprint grid, emphasizing that the code constructed this visual structure. The lighting is warm and focused, suggesting a late-night coding session. 10 point for handling errors, real-time debugging of a live application. If your code ran perfectly the first time, you are lucky. In the real world, things break. Let's simulate a common disaster. Suppose the API structure changes. Instead of a rates, the API now returns a conversion _ rates. Your process _ data function will fail. It might throw a Kira, rates, or it might return an empty data frame depending on how you wrote the code. The AI native debugging loop. Don't panic. Read the error message in the terminal. Error, Kira, rates. Verify the data. Print the JSON _ data keys before processing to see what changed. The repair prompt. User, I am getting a Kira, rates. It seems the API response keys have changed. Here is the output of print JSON _ data.keys. Update the process _ data function to handle this new key safely. This is maintenance. Code is not a static statue, it is a living organism that reacts to its environment. When you encounter an error, do not immediately ask the AI to fix it. First, use the rubber duck method. Look at the variable where the error happened. Ask yourself, is this variable empty? Is it the wrong type? Only when you have a hypothesis should you prompt the AI. This builds your mental model of the system. If you let the AI fix every bug without you looking at the cause, you are digging the death traps deeper. The final polish: once the app works, ask the AI to refactor the code into a single, clean class structure. User, now that the individual functions work, refactor this entire script into a Python class called currentVisualizer. Include docstrings explaining what each method does. This turns your experimental script into professional, portfolio-ready software. Author's note: I remember the first time I made a computer draw a chart from live data. I felt like a wizard. I refreshed the data, and the chart moved. That feeling of connection, that you can reach out into the digital ether and pull back information, is the spark that drives every great engineer. Hold on to that feeling. It will get you through the frustrating days. You have now built something real. You have moved from blueprint to reality. In the next chapter, we will expand this isolated script into a larger system, exploring how to design software that spans multiple files and databases. Figure Mind Map, Chapter 10, Building Your First App, Root, Building Your First App, Branch, Phase 1, Context and Setup, Node, Understanding APIs, Note, the Menu Waiter Analogy, Node, the Request Library, Note, Connecting to the Internet, Node, Concept First Prompting, Note, Ask, how does this work, before write this, Branch, Phase 2, Data Transformation, Node, Pandas Library, Note, Excel for Python, Node, the Data Frame, Note, Converting JSON to Tables, Node, Cleaning Data, Note, Sorting, Filtering, Handling Missing Values, Branch, Phase 3, Visualization, Node, Matplotlib, Note, Visual Storytelling, Node, Intent Specification, Note, Defining Axes, Colors, and Titles specifically, Node, the Result, Note, a visual rendered from code, Branch, Phase 4, Debugging and Refactoring, Node, Handling Errors, Note, Keras, Connection Timeouts, Node, Rubber Ducking, Note, Form a Hypothesis before Prompting, Node, Refactoring, Note, Moving from Scripts to Classes. Chapter 11, Scaling Up, System Architecture and Design. Sections. Section 11.1, Escaping the Single File, Organizing Multi-Module Projects. Section 11.2, Connecting the Pieces, Databases, Backends, and Frontends. Section 11.3, Understanding APIs and Asynchronous Communication. Section 11.4, Orchestrating the Stack, How Discrete Systems Talk to Each Other. In Chapter 10, you experienced the thrill of seeing your code come to life. You watched a Python script fetch data, crunch numbers, and paint a chart on your screen. It was a victory. But if you look closely at that file now, you might notice something unsettling. It is likely a long, scrolling wall of text. Your API keys are mixed in with your math functions, your visual styling is tangled up with your data fetching logic. In the industry, we call this spaghetti code. When you are building a doghouse, you can nail boards together wherever they fit. But if you try to build a skyscraper that way, it will collapse before you reach the third floor. Software architecture is the art of moving from the doghouse to the skyscraper. As an AI native developer, this is your most critical pivot point. LLMs are notoriously bad at managing massive, single files. They lose context, hallucinate variables, and truncate outputs. To build professional-grade software, you must stop thinking in lines of code and start thinking in systems. We are now going to learn how to break your application into distinct, communicating pieces, a discipline known as system design. 11.1 Escaping the Single File, Organizing Multi-Module Projects. The first step in scaling up is modularity. Beginners often keep adding functions to main.py until the AI refuses to process the prompt because the file is too large. Think of your code like a physical home. In a studio apartment, a single file, your bed is next to the stove, which is next to your desk. It's functional, but messy. As your life gets more complex, you need walls. You need a bedroom for sleeping, a kitchen for cooking, and an office for working. In software, we create these rooms using distinct files and folders. This is called separation of concerns. The blueprint of a modern project. Instead of one giant file, a healthy project separates responsibilities. The logic layer, utils.py or services, this is where the math happens. It doesn't know about the user interface, it just processes data. The data layer, models.py or db, this handles saving and loading information. The presentation layer, app.py or UI, this draws the buttons and charts. The configuration.env or config.py, this stores secrets like API keys, which we discussed in Chapter 9 regarding security. When you prompt an AI, you must explicitly ask for this structure. Do not ask, add a feature to calculate averages. Instead, use a concept-first prompt, Chapter 4, to dictate the architecture. The architectural prompt, I need to add an averaging feature. Do not put this in the main UI file. Create a new file named statistics_engine.py. Write the logic there, and then show me how to import that function into my main application. The magic of imports. How do these separate files talk to each other? They use a mechanism called importing. When you verify AI code, look for the top of the file. You will see lines that act as bridges between your isolated islands of logic. Hash in your main app.py file. Hash this tells Python, go look in the statistics_engine file. Hash find the calculate_average tool and bring it here. From statistics_engine import calculate_average. Data equals 10, 20, 30. Result equals calculate_average, data. By forcing the AI to modularize your code, you reduce the cognitive load on the model. You can paste just statistics_engine.py into the chat window to debug a math error without confusing the AI with unrelated code about button colors or window sizes. Figure, extra detailed AI-ready prompt for AI-generated diagram showing an exploded view of a software project. Visual style, isomeric technical drawing, blueprint aesthetic. Central element, a chaotic knot of wires labeled spaghetti code, single file, transforming into a neat stack of distinct, glowing cubes labeled UI, logic, database, and config. Arrows show clean data flow between the cubes. Lighting should be clean, cyan and white, emphasizing order and structure. 11.2 Connecting the pieces, databases, backends, and frontends. Once you escape the single file, you encounter the stack. Professional software is rarely just one program running on one machine. It is usually a conversation between three distinct entities, the front end, the back end, and the database. The best analogy for this relationship is a restaurant. The front end, the dining room, this is what the user sees. It's the menus, the tables, and the decor. In software, this is your HTML, CSS website or your mobile app interface. It looks pretty, but it doesn't cook the food. The back end, the kitchen, this is where the work happens. The kitchen is hidden from the customer. It receives orders, chops ingredients, processes data, and cooks the meal. The kitchen is secure, customers aren't allowed to walk in and grab a steak from the fridge. The database, the pantry or walk-in fridge, this is where the raw ingredients are stored for the long term. The kitchen, back-end, fetches ingredients from the pantry, the database. The dining room, front-end, never talks to the pantry directly. Why this separation matters for AI coding. If you ask an AI to build a Facebook clone in one go, it will fail. You must use atomic decomposition, Chapter 6, to build these layers sequentially. Step 1. Ask the AI to design the database schema, organizing the pantry. Create a SQL table structure for users and posts. Step 2. Ask the AI to write the backend API, setting up the kitchen. Write a Python function that accepts a new post and saves it to the database. Step 3. Ask the AI to build the frontend, designing the dining room. Build a web page with a form that sends the post data to the Python function. By respecting the separation of the stack, you ensure that if you want to redecorate the dining room later, change the UI, you don't have to rebuild the kitchen, the logic. 11.3 Understanding APIs and Asynchronous Communication. We established that the front-end, dining room, and the back-end, kitchen, are separate. So, how do they communicate? They need a waiter. In software, the waiter is the API, Application Programming Interface. When you click Submit on a website, your browser, front-end, writes down your order on a slip of paper and hands it to the API. The API runs to the server, back-end, delivers the message, waits for a response, or not, and brings back the result, the food. The concept of JSON. The language the waiter speaks is usually JSON, JavaScript object notation. It doesn't matter if your back-end is written in Python and your front-end is in JavaScript, they both agree to speak JSON. It looks like this. Order_ID, 123. Item, burger. Modifiers, no onions, extra cheese. As an AI native developer, you will frequently ask the AI to parse this JSON or format this request as JSON. It is the universal shipping container of the internet. Asynchronous, don't freeze the waiter. Here is a critical concept, asynchronous communication. Imagine if, after you ordered your coffee, you were physically unable to move, speak, or look at your phone until the barista handed you the cup. You would be frozen. That is synchronous blocking code. In modern systems, we use asynchronous, async, code. You order the coffee, receive a receipt, a promise, and then go sit down and read a book. When the coffee is ready, the barista calls your name. When prompting for APIs, you must explicitly ask for async patterns to keep your app responsive. Write a JavaScript function to fetch user data. Use async for wait syntax so the user interface doesn't freeze while waiting for the database to respond. 11. For orchestrating the stack, how discrete systems talk to each other. We now have a front-end file, a back-end file, and a database. They are living in different rooms. How do we turn the lights on? This phase is called orchestration. It is the most common point of failure for beginners because it involves invisible plumbing, ports, environment variables, and local servers. Ports, the apartment numbers. Every program running on your computer needs a unique address, called a port. Your database might live at localhost 5432. Your backend API might live at localhost 8000. Your front-end website might live at localhost 3000. If you try to run your backend on port 3000 while the frontend is already there, the computer will throw an error, dryness. This is like two people trying to live in apartment 3000 at the same time. The glue, environment variables. You should never hardcode these addresses. If you write fetch, localhost 8000 inside your code, your app will break when you move it to the cloud, where localhost doesn't exist. Instead, we use a .env file, a simple text file that acts as a switchboard. #env file. Database_URL equals postgres / localhost 5432 in my app. Backend_port equals 8000. API_key equals secret_123. Your code then asks the system, where is the database, and the system reads the .env file to answer. The orchestrator's role. As the architect, your job is to verify connections. When the AI generates code, scan it for hard-coded values. Bad AI output, connection equals connect, password 123. Good AI output, connection equals connect, os.getenv, db_password. If the AI gives you the bad version, correct it immediately, refactor this to use environment variables. Do not hardcode secrets or ports. By mastering orchestration, you move from someone who writes scripts to someone who builds platforms. You are no longer just typing code, you are city planning. You decide where the roads go, how the power lines run, and how the traffic flows. This architecture, front-end, back-end, database, API, is the standard for 99% of web applications. Once you understand this pattern, you can build anything from a to-do list to a social network. The complexity grows, but the blueprint remains the same. Figure mind map, system architecture and design, root, system architecture, branch, modularity, node, separation of concerns, node, imports exports, node, file structure, logic versus data versus UI, branch, the stack, node, front-end dining room, node, back-end kitchen, node, database, pantry, branch, communication, node, APIs of the waiter, node, JSON payload, node, async for wait, non-blocking, branch, orchestration, node, ports addresses, node, environment variables.env, node. Localhost. Chapter 12, Launching Your Career as a System-Aware Engineer. Sections. Section 12.1, The New Junior Profile, System Awareness versus Syntax Fluency. Section 12.2, Navigating the Technical Interview in the Age of Generative AI. Section 12.3, Building a Proof-of-Work Portfolio that Demonstrates Orchestration. Section 12.4, Future-Proofing, Staying Adaptable as Models Evolve. We have reached the summit of our journey. You have moved from the initial anxiety of the blank page to understanding the CIVE framework. You have wrestled with logic, verified AI outputs, managed version control, and orchestrated the architecture of a real application. Now, we face the final, pragmatic frontier, the job market. If you read the headlines, you might believe that the entry-level software engineering role is dead. Tech pundits often claim that because AI can write code, companies no longer need junior developers. This perspective is not just pessimistic, it is fundamentally incorrect. The market does not need fewer developers, it needs a different kind of developer. The era of the ticket taker, a junior who silently picks up a small bug report, fixes 3 lines of CSS, and pushes code without understanding the broader system, is indeed ending. That work is now cheaper and faster to automate. But in its place, a new role is emerging, the system-aware engineer. Employers are desperate for professionals who can look at a problem, architect a solution using AI tools, verify the safety of that solution, and deploy it. They need orchestrators, not just typists. This chapter is your playbook for positioning yourself as an invaluable asset in this new economy. 12.1 The New Junior Profile, System Awareness versus Syntax Fluency. In the past, a junior developer was judged by their syntax fluency. An interview might ask you to write a bubble sort algorithm in Java on a whiteboard without looking up documentation. If you forgot a semicolon or mixed up a variable type, you failed. Today, that test measures a skill that has been commoditized. Syntax fluency is now free. The new metric for hiring is system awareness. This is the ability to understand how different components of an application, databases, APIs, user interfaces, and authentication systems talk to one another. It is the ability to see the skyscraper, not just the pile of bricks. Figure, a comparative infographic. On the left, labeled the old junior, a figure focuses on a single puzzle piece with a magnifying glass. On the right, labeled the AI native junior, a figure stands before a completed puzzle, holding the box cover, the plan, and directing robotic arms to place the pieces. The visual style should be clean, isometric vector art. As a system-aware engineer, your value proposition changes. You are no longer selling your ability to type code, you are selling your ability to deliver outcomes. When you speak to a hiring manager, you should not say, "I know how to write React components." Instead, you should say, "I know how to use AI to rapidly prototype user interfaces and connect them to secure backends." This shift requires you to think like a general contractor rather than a specialized mason. A general contractor doesn't need to lay every brick personally, but they must know immediately if a wall is load-bearing or if the plumbing is installed backward. Your junior status does not mean you are helpless. In fact, because you learned with the CIVE framework, you likely have better habits than a senior developer who is lazily copy-pasting from ChatGPT without verification. You understand the risks of hallucination, and you know how to audit the machine. 12.2 Navigating the Technical Interview in the Age of Generative AI. The technical interview process is currently in a chaotic transition. Some companies still cling to the old whiteboard style, while forward-thinking organizations are adopting practical assessment models. You need to be ready for both, but you must approach them with an AI-native mindset. If an interview allows you to use AI tools during the assessment, do not fall into the trap of silence. Many candidates paste the question into an LLM, stare at the screen for 30 seconds, and then paste the answer back. This is an immediate failure. The interview is not testing the AI, they are testing you driving the AI. You must vocalize your context engineering, the C in CIVE. Speak out loud, I am going to instruct the model to set up a Python environment for data analysis. I'm explicitly telling it to handle edge cases for null values because I see the dataset has gaps. If the AI generates code that looks perfect, do not accept it immediately. Perform your verification, the V in CIVE, out loud. Say, the AI suggests using a recursive function here, but I'm concerned about Stack Overflow if the data gets too large. I'm going to ask it to refactor this into an iterative loop. This demonstrates that you are the pilot. You are showing the interview that you are a risk-aware operator who uses AI as a power tool, not a crutch. Even in interviews that forbid AI tools, your system awareness gives you an edge. Instead of panicking about syntax, focus on the pseudocode and logic. Explain the data flow. Most reasonable interviews today care more about your ability to structure the logic than your ability to remember whether a Python list uses .push or .append. 12.3 Building a proof-of-work portfolio that demonstrates orchestration. A GitHub profile filled with generic to-do list apps or weather widgets is no longer impressive. Millions of people can generate those in seconds. To stand out, your portfolio must demonstrate orchestration. You need to show that you can glue disparate systems together to solve a novel problem. An orchestration portfolio piece typically involves 3 layers. 1. An input source, a user form, a webhook, or a scheduled task. 2. A processing logic, where you use code, often AI-generated, to manipulate that data. 3. An output action, sending an email, updating a database, or posting to a separate API. For example, instead of a simple blog, build a content curator. Create a system that pulls the latest news from an API, uses an LLM via the OpenAI API to summarize the articles into a newsletter format, and then emails it to a list of subscribers using an email service like SendGrid. This project proves you can read documentation for multiple distinct tools and make them interoperate. It shows you understand API keys, data formatting, and error handling. Figure, a schematic diagram of a proof-of-work portfolio project. The diagram shows data flowing from a news API into a central Python script labeled orchestrator, passing through an LLM summarizer, and finally exiting to an email service. The connections are highlighted to show data transformation at each step. Crucially, you should include an orchestration log in your project's README file. Document the hardest bug you faced. Did the AI give you a hallucination that broke the database? How did you catch it? How did you debug it? Employers love these war stories. Writing, I spent for hours fighting a CORS error because the AI assumed I was using an older version of the framework, proves you have been in the trenches. It validates that you are a builder, not just a prompter. 12 Point for future-proofing, staying adaptable as models evolve. We must end with a reality check. The tools you used in Chapter 3 will be obsolete within 2 years. The specific version of the LLM you are using today will be looked upon as quaint and slow very soon. If you attach your identity to a specific tool, I am a ChatGPT expert or I am a React developer, you are building your career on shifting sand. The only way to future-proof your career is to double down on the fundamentals we covered in Chapter 7 and the rigorous process of the CIVE Framework. Context, intent, verification, and execution are timeless. The need to define a problem clearly, intent, and ensure the solution works, verification, will exist whether we are using keyboards or neural interfaces. You must cultivate a mindset of just-in-time learning. In the past, you learned a skill in case you needed it. Now, you learn a skill when you need it. When a new AI model releases that can handle video input or generate 3D architecture, do not be intimidated. Apply your framework. How do I provide context to this new model? How do I verify its output? The interface changes, but the engineering discipline remains the same. You are entering the industry at a historical inflection point. The barrier to entry for creation has never been lower, but the bar for quality is rising. By mastering the ability to guide these powerful systems, you are positioning yourself as the human anchor in a sea of automated content. You are ready. The syntax is handled. The system awaits. Go build something that matters. Figure Mind Map of Chapter 12, Launching Your Career as a System-Aware Engineer, Root, Launching Your Career, Branch, the New Junior Profile, Node, System Awareness, Leaf, Understanding Connections, Leaf, General Contractor versus Bricklow, Node, Syntax Fluency, Leaf, Commoditized Skill, Leaf, No Longer the Differentiator, Branch, the AI Interview, Node, Using AI Tools, Leaf, Vocalize Context Engineering, Leaf, Verify Out Loud, Node, Driving the Machine, Leaf, Pilot vs. Passenger, Leaf, Risk Awareness, Branch, Proof of Work Portfolio, Node, Orchestration, Leaf, Connecting Multiple APIs, Leaf, Input-Process-Output, Node, Documentation, Leaf, Orchestration Logs, Leaf, Specific Debugging Stories, Branch, Future-Proofing, Node, Just-in-Time Learning, Leaf, Adaptability over Memorization, Node, CIVE Permanence, Leaf, Logic Outlasts Tools, Leaf. Verification remains crucial. Conclusion: the human element in a synthetic world. Sections. Section 13.1, Summarizing the CIVE Framework and Key Takeaways. Section 13.2, The Ethical Responsibilities of the AI Native Developer. Section 13.3, Final Encouragement, You are the architect, AI is the tool. Section 13.4, Next Steps, Continuing your education beyond this book. When you first opened this book, you were likely standing on one side of a vast chasm. On your side was the desire to build, to create software, launch apps, and automate tasks. On the other side was the terrifying wall of syntax, semicolon errors, obscure compiling issues, and the daunting belief that you needed to memorize a dictionary's worth of commands before you could write a single line of code. We have crossed that chasm together. But we did not build a bridge of memorization. Instead, we built a bridge of orchestration. Throughout these chapters, you have moved from the passive confusion of vibe coding to the active command of the CIVE framework. You have learned that in the era of Software 3.0, the value of a developer is not measured by their typing speed or their ability to recall the parameters of a specific Python function. It is measured by their ability to think clearly, describe intent rigorously, and verify output skeptically. As we close this guide, we must address the most important variable in the equation. It is not the large language model. It is not the IDE. It is you. In a world increasingly filled with synthetic text and generated logic, the human element is no longer a soft skill, it is your primary competitive advantage. This conclusion is not just a summary, it is your mandate for the future. 13.1 The CIVE Framework, a retrospective. We began this journey by dismantling the myth that you need to compete with the machine. We established a new methodology designed specifically for the AI native developer. Let's briefly crystallize the CIVE framework one last time, looking at it not as a set of steps, but as a professional philosophy. Context is control. You learn that an AI without context is a hallucination waiting to happen. By mastering context engineering, you move beyond asking, "How do I code this?" to asking, "How do I teach the AI to help me code this?" You learn to prime the model with your constraints, your skill level, and your architectural goals. You stopped treating the AI like a magic 8-ball and started treating it like a junior teammate who needs a clear briefing. Intent is architecture. We realized that code is cheap, but intent is expensive. Through intent-driven specification, you learned that ambiguity is the enemy. By defining your inputs, outputs, and edge cases before a single line of code was generated, you practiced the true discipline of software engineering, logical problem solving. You learned that if you cannot describe the logic in plain English or Gherkin syntax, the AI cannot write it in Python. Verification is survival. Perhaps the most critical lesson was the danger of the AI death trap. Verification-driven development taught you that trust is earned, not given. You learned to use the build, delete, rebuild loop to ensure you weren't just renting knowledge, but owning it. You learned to read code not to write it, but to audit it, hunting for security flaws and logic gaps that the probability engine of an LLM might gloss over. Execution is atomic. Finally, you learned that Rome wasn't built in a prompt. Execution and atomic decomposition showed you how to break massive, terrifying projects into small, solvable scripts. You moved from the spaghetti code of a novice to the modular architecture of a system-aware engineer. Figure, extra detailed AI-ready prompt for AI-generated diagram showing a circular feedback loop. The center of the circle is a stylized human silhouette labeled the orchestrator. For quadrants surround the human, 1. Context, input data streams, 2. Intent, blueprints schematics, 3. Verification, magnifying glass is shield, 4. Execution, gears are building blocks. Arrows flow clockwise, but double-headed arrows connect the human to every quadrant, emphasizing central control. The style should be clean, vector art, tech blue and white palette. 13.2 The ethical responsibilities of the AI native developer. With the power to generate software at the speed of thought comes a profound responsibility. In the old world, if a developer wanted to build a bot to scrape a website or an algorithm to filter job applicants, it took weeks of effort. That effort was a natural friction, a time for consideration. Today, you can spin up powerful agents in minutes. This removes the friction, but it increases the risk. As an AI native developer, you are the human in the loop. You are the moral compass of the code. The bias of the training set. You must remember that AI models are trained on the internet. They reflect the collective knowledge of humanity, but also our collective biases. If you ask an AI to generate an algorithm for sorting user data, it might inadvertently introduce bias based on historical patterns it learned during training. You cannot blame the AI for this. The AI is a statistical engine, not a moral agent. It is your job to audit the logic. Ask yourself, does this code treat all users fairly? Are we making assumptions about data that might exclude certain groups? Security and liability. When you copy-paste code into production, you own that code. If the AI suggests a database configuration that leaves user passwords exposed because it was trained on insecure tutorials from 2015, you cannot tell your boss or your users, the robot did it. You are the signatory. You are the one who pushes the deploy button. This is why the verification step of CIVE is ethical, not just technical. You owe it to your users to understand what the synthetic code is doing with their data. The stewardship of the internet. We are currently seeing a flood of low-quality, AI-generated spam apps clogging app stores and the web. Do not contribute to the noise. Use your new skills to build software that solves real problems, adds value, and respects the user's time. Be a craftsman, not just a content mill. 13.3 Final encouragement. You are the architect, AI is the tool. There is a lingering fear among many beginners that they are learning a skill that is about to become obsolete. Why learn to code, they ask, if the AI will just do it better in 5 years? This perspective confuses the act of coding with the art of engineering. Hammers have been improved for centuries. We went from rocks to iron to pneumatic nail guns. Yet, we still need carpenters. In fact, because nail guns allow carpenters to work faster, we can now build structures that were previously impossible. AI is your pneumatic nail gun. The shift from how to why. For 50 years, software engineering was constrained by the how. Asterisk, how do I center this div? Asterisk, how do I allocate memory for this array? Asterisk, how do I write a sorting algorithm? The AI solves the how. This liberates you to focus entirely on the what and the why. Asterisk, what problem are we solving for the user? Asterisk, why are we building this feature instead of that one? Asterisk, how does this system connect to that database securely? You are no longer a bricklayer, you are the architect. The bricklayer is exhausted by the physical act of laying stones. The architect is energized by the vision of the cathedral. Your human intuition. AI models are brilliant at pattern matching, but they lack intuition. They cannot look at a user interface and feel that it is clunky. They cannot sit in a meeting with a client, read the room, and realize that what the client said isn't what they need. Your humanity, your empathy, your frustration with bad tools, your desire for beauty and efficiency is the spark that drives innovation. The AI can write the code to paint the canvas, but you must choose the subject. 13 point for next steps, continuing your education beyond this book. Closing this book is not the end of your education. In the tech industry, if you stop learning for 6 months, you are effectively moving backward. However, you do not need to chase every new AI tool that launches on Product Hunt. Here is a sustainable roadmap for your post-book journey. 1. Deepen your system design knowledge. Since you don't need to memorize syntax, spend that mental energy on system design. Learn how the internet works at a high level. Asterisk, study DNS, HTTP, and API protocols. Asterisk, learn about cloud architecture, AWS, Azure, Google Cloud. Asterisk, understand database design, SQL versus NoSQL. Asterisk, resource, read Designing Data-Intensive Applications, once you feel ready for a challenge. 2. Master soft skills, which are now hard skills. As coding becomes commoditized, communication becomes premium. Learn to write clear technical documentation. Practice explaining complex logic to non-technical stakeholders. The developer who can bridge the gap between the RA's output and the business's goals will always be employed. 3. Build toy projects constantly. Keep your build, delete, rebuild loop active. Asterisk, build a personal portfolio site. Asterisk, build a tool to automate a spreadsheet task at work. Asterisk, build a simple game for your kids or friends. Do not worry if these projects are messy. The goal is to encounter new errors so you can practice fixing them. 4. Join the community. Software 3.0 is new for everyone, even senior engineers. Join Discord servers, Reddit communities, or local meetups focused on AI engineering. Share your prompts. Share your failures. We are all figuring out the new rules together. The final word. The timeline of technology is long, but you have entered it at a singular, golden moment. The barrier to entry has never been lower, yet the ceiling for what you can create has never been higher. You have the framework. You have the tools. You understand the risks. The screen is blank, but you are no longer afraid of it. Open your editor. Initialize your agent. Build something wonderful. Figure mind map the AI native developer's journey from concept to conclusion route, the AI native developer branch, the CIVE framework sub, context, the setup, sub, intent, the blueprint, sub, verification, the safety net, sub, execution, the build, branch, ethical responsibility sub, human in the loop sub, bias auditing sub, security ownership sub, quality stewardship branch, the new mindset sub, architect typist sub, why how sub, empathy syntax sub, orchestration memorization. Branch, continuous growth sub, system design sub, communication skills sub, toy project sub, community engagement. Chapter 14, Beyond the Book, Becoming a Lifelong AI Native Engineer. Sections. 14.1 From Knowledge to Identity, Making the Shift Permanent. 14.2a Personal Operating System for AI-Assisted Development. 14.3 Signals employers actually care about in the AI era. 14. For your 90-day roadmap after finishing this book. 14.1 From Knowledge to Identity, Making the Shift Permanent. Finishing this book does not make you a developer. It makes something far more important possible. It gives you the opportunity to change your identity. Many people read technical books the way they read travel guides, interesting, informative, and quickly forgotten. They absorb concepts intellectually, but nothing about their daily behavior changes. That is not enough in the age of AI. To succeed long-term, you must move from knowing the CIVE framework to being a CIVE engineer. That means you instinctively define context before asking for help. You refuse to accept vague intent. You verify outputs even when they work. You execute in small, testable units. This is no longer something you do. It is how you operate. Once this identity shift happens, you stop asking, "What tool should I learn next?" and start asking, "What system am I trying to design?" That question will never go out of date. 14.2a Personal Operating System for AI-Assisted Development. Every professional operates according to an invisible system. Some developers operate on panic, tutorials, copy-paste, trial and error. You now have the opportunity to operate on something better. Think of CIVE as your personal operating system, POS, for building with AI. Whenever you sit down to work, consciously or unconsciously, you should pass through the same internal checklist. Context check. Do I understand the environment? Do I know the constraints? Does the AI know what I know? Intent check. Can I clearly describe the behavior? Have I defined success and failure? Do I know what done means? Verification check. Could I explain this logic to another human? What assumptions does this code make? What breaks first? Execution check. Is this the smallest meaningful unit? Can this be tested independently? Am I building or just generating? This mental loop should become automatic. When it does, you stop fearing new technologies because you no longer depend on them to think. 14.3 Signals employers actually care about in the AI era. A quiet truth is emerging in the hiring market. Everyone now has access to AI. Very few people know how to use it well. Employers are no longer impressed by built with ChatGPT, AI-powered app, generated using GPT-4. Those are table stakes. What they look for instead are signals, evidence that you can be trusted in a high-leverage environment. Signal number 1, you can explain your decisions. If asked, "Why did you design it this way?" you have a real answer. Not, "That's what the AI suggested. That's how the tutorial did it." But, "This minimizes coupling. This isolates state. This reduces risk." Signal number 2, you treat AI output as drafts, not truth. You show iterations, refactors, tests, corrections. This tells employers you are not fragile. Signal number 3, you think in systems, not files. You understand data flow, state boundaries, interfaces, failure modes, even in small projects. That is the difference between a junior developer and an engineer in training. 14 point for your 90-day roadmap after finishing this book. To turn this knowledge into momentum, here is a practical, realistic 90-day plan. No hype. No overwhelm. Days 1 to 30, reinforcement. Your goal is habit formation, not scale. Build 3 to 5 very small projects. Use CIVE explicitly, write it at the top of your notes. Delete and rebuild at least one feature per project. Write simple tests, even if they feel redundant. Focus, thinking clearly with AI. Days 31 to 60, integration. Now introduce mild complexity. Add APIs. Add state persistence. Split projects into multiple files. Refactor something that already works. Focus, system awareness. Day 61 to 90, proof. Now think like a professional. Choose one project. Polish it. Document decisions. Show verification steps. Explain trade-offs in writing. This becomes the foundation of your portfolio. Focus, trustworthiness. The final perspective. The AI era is not about speed. It is about leverage with responsibility. The developers who thrive will not be the ones who generate the most code, but the ones who design the clearest intent. Catch errors early. Understand systems deeply. Adapt calmly as tools change. You are now equipped to be one of them. This book did not teach you how to code faster. It taught you how to remain valuable in a world where code is abundant. That is the real skill.